observe
okay,
the chat probably.
I'll follow the chat and I would read the questions.
Actually, it's a very nice meeting, well organized, fantastic program.
Yes, I noticed that you participated a few talks in the school. You attended also.
Yeah.
Yes. Okay. So people are still joining. So let us wait for another minute or so.
Okay, it's fine.
Okay, let's get started. So welcome everyone to the ICTS discussion meeting on trapped atoms, ions, and molecules. This is a 3-day conference or meeting. So today is the first day. And in the first session, our speaker is Professor Rudolf Grimm. And this meeting is a follow-up of the school that we had last week and the week before. So we had about 8 days school on the same topic. So to introduce Professor Rudolf Grimm, it's a great pleasure to introduce and welcome Professor Rudolf Grimm. Professor Grimm is the head of the Institute of Experimental Physics at University of Innsbruck and research director at Institute of Quantum Optics and Quantum Information, Austrian Academy of Sciences, Innsbruck. He is also a member of the Committee of Experts for the German Excellence Strategy, Germany. He received many awards and honors. I'm not going to mention all of them, but I would name a few of them. He received Fagdib Medal of the American Physical Society and European Research Committee on Few Body Problems in Physics in 2018. He received Austrian Scientist of the Year in 2009. He also received Gerhard Hess Award of the German Research Foundation in 1996. So with this brief introduction, may I invite Professor Grimm to present your talk. Thank you.
Okay, first of all, thank you very much for the kind invitation to this meeting. I enjoyed it already. I attended some of the lectures. It's a very good program, very well organized. I'm really happy to join. It's a lot of fun. And let me now share my screen. Here we go. Okay, now you should see my title slide. Hope it's okay. I give you some impression of Innsbruck. That's where we live and do our research. As mentioned in the introduction, we have 2 institutions, a university and an Academy of Science Institute. And we are located, it's not on the photo, in the lower right corner, a little bit further outside of the city. It's a city center. And you see a little bit our nice mountains. Okay, so the subject of my talk are ultra-cold fermion mixtures. And I hope to convince you that it's really exciting to study interactions in these fermion mixtures, and this is really what makes them or the field strong interactions in fermion mixtures. So the fermions have a big advantage as compared to the bosons. They offer usually a much better stability than the bosons because of few body process and Pauli suppression. So fermions in strongly interacting regime usually live longer. So let me switch to the first slide where I introduce some key players. These are atoms we work with. We work with 3 different kinds of fermions: lithium-6, potassium-40, and also dysprosium-161. But we also work with one boson, and here's Bose, with the potassium-41 isotope. Okay, in the first part of my talk, I will speak about this one, and it's about mixtures of lithium-6 with either fermionic potassium or bosonic potassium. And the subtitle is Polarons in Different Interaction Regime. We are interested in the physics of impurities, mainly the Fermi polaron. In the second part of my talk, I will speak about a new mixture of fermions, potassium-40 plus dysprosium-161. And here the main goal is to create novel superfluids in mass imbalanced mixtures. Okay, now let me switch to this slide. Here I try to explain the general research question in our Fermi-Bose experiments, so bosonic impurities in a Fermi gas. And here is just a kind of sketch of a Bose-Fermi mixture. The red ones are the bosons, the blue ones are the fermions. And what is very well investigated, what has been very well investigated are the extreme regimes, and in particular the Fermi polaron, where you have a single impurity particle in a large medium of the other ones. Or the opposite case would be you have a bosonic medium and a single fermion impurity. So the Fermi polaron has been very, very well investigated. The Bose polaron has also received quite some attention. It's a bit more difficult because the system tends to decay faster. And in the center is a balanced mixture. And how do we investigate now the system? I mean, the central question is, how are these worlds connected? What happens if I change, let's say, the concentration of the bosonic particles? Then I get an equal mixture, and then it's the Bose polaron regime. Well, our approach is to study this regime, to fill the gap, and to study the regime where you have, let's say, a few interacting polarons in the medium here and then. And that's our general research approach, to study finite concentration effects, impurity interactions, or mediated interactions. So that's now the main focus of our work, to understand impurity interactions, mediated interactions in this situation. So that is the general research question. Now let me introduce our system in a very simplified way. So we use with an optical trap formed by an infrared laser beam. And in this infrared laser beam, we create a Fermi sea of lithium-6 atoms. So this is quite standard, how to cool lithium-6 to degeneracy and so on. At the end, we have a Fermi sea, all atoms in the lowest spin state, few times 10 to the 5 particles. And so the temperatures are somewhere between 15 and 20% of the Fermi temperature here. Okay, then we put in impurities. In the impurity atoms, we have the choice of potassium-40 fermion or potassium-41, a boson. These are typically 10 to 20 times less particles. And the local concentration, the density ratio in the trap center, is something like 10% or up to 50%. So potassium over lithium. Well, that's the situation that we investigate. Good, so let me switch to this one. Okay, yes, of course, very important. We have the possibility to tune the interaction between the impurities and the Fermi sea by a Feshbach resonance, which makes the interaction really, really very strong. Good, so here is some slide that explains our way to probe the sample. And we use radio frequency spectroscopy, in particular injection spectroscopy, I will explain in a minute. And we have 2 different spin states, hyperfine Zeeman substates. And we can couple by radio frequency. Okay, now the point is that we choose a situation where the lower state is just weakly interacting with the lithium-6 medium, basically not interacting, just enough interaction to make the sample thermalize. And we couple this to another state, and this state is a state which has a strong interaction or tunable strong interaction with the lithium-6 medium. So in this state, the system has the Feshbach resonance. And for potassium-41, this is at 157 Gauss. For potassium-40 at 335 Gauss. Now I see now it's wrong. It's just the other way around. This is 335. This is 157.4. Sorry for that mistake. And there you find the Feshbach resonance, which is about 1 Gauss wide. And it's a nice thing that these two resonances we have in the bosonic and the fermionic impurity system have almost the same character, almost the same width. So if you change the isotope, the only thing that you change is the quantum statistics of the impurities. So the Feshbach resonance physics, the subtle Feshbach resonance physics regarding effective range and so on, stays exactly the same. Good, so now I have to explain injection spectroscopy. If we start with a weakly or non-interacting state, and we drive the system in the strongly interacting state, we can probe the spectral function. So this state, it's no longer the bare state, it's somehow broadened and has some structure. And this can be probed by the radio frequency transfer, this injection spectroscopy. In contrast to ejection spectroscopy, where you prepare the strongly interacting system and then drive the system into non-interacting states. It gives a little bit different information. For us, these ways are the way to go. A few remarks, technical remarks on the pulses. We work with, in the system, if there's no interaction, we put the RF power such that we just drive pi pulses to optimize the signal. The pulses are 1 millisecond long, which gives us a spectral resolution of 7 kilohertz, which is 4% of the Fermi energy. So on the interesting energy scale, the Fermi energy, we can very well resolve what is going on. But it's good to be fast for reasons that will become obvious in a few minutes. Good, so the interaction is characterized by an interaction parameter. We just call it capital X, and this is minus 1 over the Fermi wave number times the scattering length, the dimensionless parameter. And the Fermi wave number characterizes the interparticle distance. It's just the inverse interparticle distance related to the Fermi energy by this expression here, by this well-known expression. The Fermi wave number in our system is, just to give you a number, the inverse Fermi number is about 4,000 times the Bohr radius, which tells you if you want to make this strongly interacting, you want to have the interaction parameter small or comparable with 1, then you need large scattering lengths, and this is given by the Feshbach resonance. So we get into the strongly interacting regime if we can achieve scattering length larger than 4,000 times the Bohr radius. And this is possible, but I have to make this remark. It's a little bit technical, but nevertheless important. To enter the strongly interacting regime, we have to control the magnetic field on a level of something like 10 milligauss on top of 300 Gauss. So it's quite challenging, and it's not very easy to do this. So it's a lot of work went into that to control the magnetic field accurately. Good, so now I'm ready to show a first spectrum. And this is a spectrum we took now almost 10 years ago with fermionic impurities. Few fermionic impurities in the Fermi sea. And we see if we vary the interaction parameter, this is interaction parameter called X. And then you see there are two branches. There's a branch at positive scattering length where the energy of the system goes up. And here the energy goes down. This is the attractive polaron, and this is the repulsive polaron here. And then it gets in the center, it gets a bit complicated. If you want to ask yourself, oh, sorry, this is what I forgot to mention. I mean, this polaron spectrum is quite well understood. And I just want to mention our long-standing theory collaboration with Pietro Massignan from Spain and Georg Bohn from Denmark. And we see here that the theory based on a T-matrix approach and single particle hole excitation, so higher order particle hole effects are neglected, captures the energy spectrum very, very well. So this is the calculated repulsive polaron and the attractive polaron. And that in the center, it's more complicated. Here you can excite you can excite pairs and particular molecules. Good. If you ask yourself what happens here in the center, then it's a bit complicated. And to see something, you have to increase your radio frequency dramatically, also increase the available energy scale, and then it looks like this. Very colorful. Here in this graph, you don't see any structure, but there is structure indeed, and one still sees kind of a interference between the repulsive and attractive polaron, but this is not the story of today. If you want to learn about this, I refer you to this publication. Okay, the story today is again about the polarons, where they are well resolved still. Yet still, if you look in the spectrum, for example, here it's the repulsive polaron, and here's the corresponding spectrum, just going along this dashed line. And looking at the signal, you see there's a polaron peak, the quasi-particle peak, which tells you how much wave function of the bare particle is in the polaron wave function, and then the broad pedestal of the width, roughly the Fermi energy, which shows excitations, the dressing cloud of the polaron. You see it in the repulsive case, you see the same thing in the attractive case. But we focus on the repulsive case in our work. Here, the system has lifetime. Somewhere here, it has 100 milliseconds, 10 milliseconds, and here it has at least a millisecond. The millisecond is still long enough so that it's a well-resolved quasi-particle. So the time scale of the Fermi system, the Fermi time in the system is something like 5 microseconds. So the repulsive polaron is very well resolved, and we focus on the repulsive polaron because it's somehow easier, it's better separated from all the molecule excitations than the attractive one. This gives some complications for the attractive case. So we look at the repulsive polaron, metastable quasi-particle with lifetimes on the millisecond order of magnitude. Good, what next? Okay, a question here, Enrico Fermi. And here's a question, and this question is, in our system of potassium-40 impurities, different fermion in the Fermi sea of lithium-6, if I now change the impurity, if I replace potassium-40 by potassium-41, what happens? What is the difference? Does it make a difference? What would one expect? I mean, you would expect in the single impurity limit, if there's just one impurity particle in the Fermi sea, of course, there is no difference because quantum statistics does not matter, but maybe in the interactions physics. So we'll see. So here is again the spectrum you have seen before for the fermionic impurities, and now I compare it with a new spectrum which we took last year on the bosonic impurities under similar conditions. And you see this is different. I mean, what you see, that we used a different color scale, sorry for that. This is of course different, but if you look at the, if you look at the spectrum here, okay, no, this comes too early. Okay, I want to compare this. If you look at the polaron branches in both spectra, this one and that one, okay, you see there's essentially no difference. So the polaron spectrum looks right the same at an impurity concentration, which is, let's say, 0.2 or 0.3. Okay, so the question comes now, Fermi's follow-up question is, does really nothing change if I replace the fermion impurities by the bosons? Now let me give an experimental answer. You have seen this before. This is exactly the same figure I've shown before, with the red dashed lines, the polaron spectrum, and this is where you expect a molecule to transition to a molecular system. But we focus on that one. And this was taken at a temperature of about 19% of the Fermi temperature. So the lithium Fermi sea has about 0.19. We can control it, we can cool deeper. And if we cool a little bit deeper, just a little bit deeper, then we see this one. Then we see at 14% of the Fermi temperature, oops, the spectrum develops an additional feature. And the polaronic branches are still there, but there's something else which has much less energy shift and connects somehow these two regimes. And what we see is, if, and what happens here under these conditions, now the sample is cold enough that the bosons form a condensate. And we see the emergence in the spectrum of a new branch which comes from the Bose-Einstein condensate that is formed. Now this is a thermal impurity cloud, this is a partially condensed impurity cloud, and you see both the polarons and you see this BEC branch. Okay, so what happens? Just an illustration. Now we have in the trap partial BEC, so we have three different regions. We have the large Fermi sea, we have a cloud of thermal impurities, and we have in the center a Bose-Einstein condensate. And so the different branches here, this leads to the polaron branch. A thermal saturated impurity cloud still shows this polaron spectrum. And here we have the Bose-Einstein condensate, which leads to new features. Actually, I want to make the remark that we have studied this situation in several publications, Bose-Einstein condensate in the Fermi sea, for example, for thermometry. What we have done also is we studied in particular a phase separation effect, that strong repulsive interaction. If you have a BEC, it phase separates from the Fermi sea. And here are the publications. But the point I want to make is, because of the short time scale now, the radio frequency pulse is just a millisecond long or even shorter, then the system does not have the necessary time to phase separate. There's no time to phase separate. And that means you cannot explain the features that you see with just phase separation. There's something else going on. Okay, what is going on? Now we have a situation that the BEC is very dense and has doped with a few atoms from the Fermi sea. We get here the opposite situation. Actually, in the center of the trap, we have a Bose polaron of a BEC of, let's say, 10,000 atoms or 15,000 doped with a few hundred lithium fermions, a doped BEC. And we looked into this BEC branch a little bit more closely. It's very noisy data, it's very difficult, it's small shift. And you see an energy shift as a function of the ratio of bosonic density to fermionic density. And you see, well, there is some shift, it scatters a lot and may have a trend to decrease if you decrease the boson density. And what is the red line? The red line is a simple theoretical model to estimate the interaction energy of the fermions with a bosonic mass, the interaction energy. And it's a simple back-action model. So we modeled the system as consisting of universal Bose polarons and calculate from that Bose polaron picture the interaction energy, and then calculate what is the interaction energy per potassium atom that we probe. And this gives a model like this, which I would say is at least consistent with the Bose polaron picture. Good, but you see the data has a lot of scatter, and there are technical issues. Actually, the magnetic field control, fluctuation of the interaction parameter, also the temperature was not really kept very constant in some of these measurements. And now let me look on the signal provided by the thermal bosons. And this is now the polaron shift. Now this is a polaron peak that we analyze as a function of the concentration, bosonic atoms versus fermionic atoms. This is not the Bose polaron, it's again the Fermi polaron picture. Then we see the data may show a trend to decrease a little bit, but there's a lot of scatter and there's an outlier point. It's not really clear. And this solid line here, it's a theoretical approach, a perturbative approach by a paper published a couple of years ago by Chris Pettick, a Fermi liquid picture to calculate in a perturbative approach the concentration shift. And the prediction is a small shift, downshift. Small downshift is predicted, and these error region dashed lines show how the theory changes within the uncertainty of the experimental parameters. So we can say, yeah, okay, it might be consistent with this shift, but we don't observe really a downshift. And that's the point. There may be a little downshift, but certainly not an observation. But the problem is, again, the technical issues, large fluctuations of the interaction parameter and temperature. Okay, so this is data just published in a paper, FISRFA, coming out 2 days ago. And the data were taken last year. And since then, the team in the lab has worked a lot on improving the technical things. And now I can show a new graph, which is similar to that graph. And this looks like this. Now, in a strongly interacting regime, interaction parameter minus 0.6, strongly repulsive interaction, we really see an impurity, an effect of the impurity concentration. Though the polaron shift goes down, experimental data, and the blue line is just a simple straight line. It's a linear fit to the data. So we very clearly see an interaction effect. And we can now use the blue line to extrapolate to 0 concentration, the single impurity limit, or to interpolate at any concentration. And here's now a graph which shows the black data points are as a function of the interaction parameter, the energy shift. The black points are extrapolations into the impurity, single impurity limit, whereas the red points are interpolations, that's, I think, 0.4 impurity concentration. And now you see in these curves, energy shift versus interaction parameter, clearly this shift of the interaction shift of the polaron peak. So we are quite excited by this, and I think it's a clear first observation of an energy shift induced by mediated interaction in such a Fermi polaron system. But I have to emphasize data analysis is still preliminary. So we don't have a theoretical model now for this. I mean, what we see here actually relatively close to resonance under strongly interacting conditions. It's a much stronger effect than this perturbative theory predicts. So this is something we have to sort out, again, in collaboration with our theory friends. Okay, let me summarize this part. Where do we stand? Okay, here is just again the Fermi-Bose mixture with the 2 limits, Fermi-Polaron, Bose-Polaron, the balanced mixture in the center, the system with interacting impurities. And what we have seen by going from the single impurity limit to higher concentration, a clear interaction-induced shift. It's the first observation. We have seen a glimpse of the Bose-Polaron in our system with quite noisy data. So I would not call it an observation, but we have some data which are clearly consistent with this picture. Future, we want to plan this in more detail, also vary the concentration of the bosonic bath. And of course, then in the future, we want to understand the whole connection, and in particular, the strongly interacting Bose-Fermi mixture, which has realized, which has reached actually or attracted little attention so far, probably because it's a system which rapidly decays because of few body effects. But now we have a system which we investigate on a rather short time scale. Okay, so this is not the last slide of this part of the talk. The last slide is showing the lab. So this is our lab, the IACS Institute, laser table, main machine. Now there's even more optics. The picture is a couple of years old. And this is the present team in the lab, the PhD students, Isabella, Cosetta, and Erich. Isabella took the data on the polaron, the Bose impurity in the polaron, and Cosetta is now taking the data on the frequency shifts. Erich is working on some new things. Bo is a postdoc and working on spin or Ramsey type measurements now. Emil, senior scientist, and the present speaker here. So that's the team. And I think this is now a good point, because before switching to the next part of the talk, to ask questions or to answer questions.
I have a question. So you studied the density dependence of the polaron. How about the mass ratios?
Good point.
If you substitute lithium-6 by lithium-7, what will happen?
So the I think for what I talked about in the first part of the talk, the mass ratio has more quantitative effects. I mean, the spectrum looks a bit different. The main points, molecular polaron transition is a little bit shifted. So it can have some effects, but I don't see that it introduces something completely new, the mass ratio. It's an additional degree of freedom that we have, not completely tunable, but we're choosing ratios. So the spectrum, the details of the spectrum are influenced by the mass ratio. There's theory for this, and also by the effective range of the Feshbach resonance. So and these are details, but the mass ratio will have a dramatic role in the next part of my talk. That will really introduce something qualitatively new.
I don't see any question in the chat box. But if
okay, then
any of you, okay,
then I can continue, and we discuss further questions at the end of the talk. Okay, now I switch gears a bit. I mean, just going back to Fermi, and another question is, if I have a system of only fermions, lithium-6, potassium-40, with a mass ratio. I mean, we have heard beautiful lessons by Martin Zwierlein on this lithium-6 superfluid fermion system, which is very popular in the field. Many groups are working with it, produces fantastic results. But there I have a mass ratio of 1. It's just 2 different spin states. But the question is, what happens in a Fermi-Fermi mixture if I have mass balance, what you're asking about? That's now the question. And the question is, can we create an asymmetric superfluid? Actually, creating an asymmetric superfluid, meaning with different masses, has been a long-standing dream for me already for more than 10 years. And you think that with lithium-6, potassium-40, we have an ideal system. Okay, but here are some predictions. These are more qualitative predictions, but shows you, it's a phase diagram from a paper by Henk Stoof, published in this paper. For the homogeneous case, trap is in a little bit different situation, but to set the stage, let's discuss the homogeneous system. What does it mean? P is just the polarization parameter, which is just the imbalance, population imbalance parameter. And this is, of course, in a mass balance system, it's symmetric. Okay, SF, of course, means superfluid. It's superfluid. If I have a mass balance system, it's superfluid up to a certain transition temperature where superfluidity breaks down. Okay, if I control the polarization or population balance, then I mean you get a certain region which is FR. FR is not Feshbach resonance. It is the forbidden region, which means that the system will phase separate into a paired component and a component where you have only one single species component. I forgot to mention this phase diagram is at unitarity, exactly on resonance, the strongest interaction that nature allows. Then here you get a tri-critical point, and here's the normal phase. That's a generic phase diagram, which also has been studied in experiments at MIT and also other groups. So this is kind of well established. If I apply now the same to a mass imbalance system, I get this phase diagram. If we first look on the right-hand side, where we have the majority of light particles, it looks similar. There's a forbidden region where the system phase separates, tri-critical point, the superfluid, the normal phase. Nothing really new here. But if you look at the other side, where the majority is heavy, then something extremely exciting happens. Look, there's a new feature, new point. LP stands for Lifshitz point. And this is a point where Cooper pairs become unstable and become towards finite momentum pairs. And there's again a forbidden region, but this is SS, stands here for super solid. It means in general, you can also call it FFLO phases. This is this phase where the order parameter becomes inhomogeneous in different ways. So this is where you expect this phase, below this Lifshitz point. And the very nice thing is, if you now look under the conditions, T over TF roughly, it's in a region which is experimentally accessible. You have in an experimentally accessible region very exciting things to happen. For this system also, there are some predictions on FFLO type phases, but under conditions where we have a thousands of the Fermi temperature, very exotic conditions that we cannot reach experimentally. But this is now in reach. These are conditions which seem realistic for experiments. Good. So this is another phase diagram which tells you the same story from this paper. Considering phases, it tells you again that it's interesting to work with a system where you have the majority of heavy atoms, and then there will be a Lifshitz point, and below the Lifshitz point, you get exotic phases here. So the general statement, and that's also supported by many papers, is mass imbalance favors exotic superfluid phases. That's a real qualitative difference, and that's the main motivation for our work. This is how I put it. It's our holy grail in the field to realize these FFLO type phases. Still a long way to go, but we have a very nice perspective here to do it. Good, so next slide, experiments. No, sorry. Now you think, I made you think that lithium-6, potassium-40 is an ideal system. And many of the theoretical papers have considered this mixture. But we worked on this for many, many years, and we found out some dirty secrets of the Feshbach resonances. And I don't want to go into detail through this slide, but it turns out that the lithium-potassium 40K Feshbach resonances are not very well suited for this purpose. In the resonance we usually use, there is two-body loss, because the point is, it's a combination where the potassium atom is not in the lowest spin state. So here's the lowest one for lithium, that's fine, but you have potassium in a higher spin state, and by collision, it can lose this energy, and this leads to losses. So the system is lossy because of two-body losses, and also because the usual Pauli suppression that you need near Feshbach resonance to make the system collisionally stable against few-body processes, it is there. You see a suppression here in atom-dimer collisions, but it's weak. And we understand why it is weak. It comes from the Feshbach resonance. So the conclusion for this kind of physics on superfluidity is the lithium-6 potassium-40 system is not very kind to us. The lifetime is too short. For the polaron physics, it's perfect, works wonderfully. But if you want to have a stable superfluid system, it's not the best way to do it. That was the conclusion of many experiments. That motivated search for another combination. And here you see a periodic table, and I mark the 8 elements which have fermionic isotopes which have been brought to degeneracy. So kind of a rich choice, but if you go through certain arguments, I mean, you want to have a certain mass ratio which is not too big, not too small. You want to have Feshbach resonant interactions and so on and so on. And then actually not many combinations are left over. Actually, in Florence, they are trying an experiment to combine lithium-6 with chromium-53, which looks interesting. But another interesting combination is the combination of dysprosium and potassium. Then you get a mass ratio of 4. This has 40, and this is 161 mass ratio, so mass ratio of 4, which is still a decent mass ratio for these superfluid phases, and where you can expect that the system is well coolable, and you can expect Feshbach resonances and so on. So our choice a few years ago was to set up a new experiment on these dysprosium-potassium mixtures. But the main question, if you start with a new system, you don't know anything about the interaction properties. The question is, what are the interaction properties? Are they friendly? Are they favorable? And we have to search for broad Feshbach resonances for interaction tuning. Good. Now, little sketch of some experimental procedure. We have an experiment running which can prepare dysprosium 161 isotope, potassium 40 isotope, and this shows the optical potentials in the trap. The polarizability for potassium, and that's something we measured accurately, is in an infrared trap 3.2 times larger. So the potential for potassium is always deeper, which is good, which is a good feature. And then we have, in addition, of course, gravity is larger, the effect of gravity for the dysprosium, so the potential is more tilted than that one. So if we put this mixture into an optical trap and we carry out evaporative cooling, we will see that the dysprosium atoms evaporate and the potassium atoms just stay in the trap because the potential is much deeper. So our approach, described in detail in this publication, uses the 161 dysprosium as a cooling agent. And there we have the nice effect of these dipolar species. So it has a strong magnetic dipole moment. We don't use this for the physics really, it doesn't make a big difference, but we use the elastic cross-section that results from that for evaporative cooling. So we can nicely cool a single spin component of dysprosium deep into the degenerate regime. It works really very well. And we can sympathetically cool potassium-40. Okay, and we found that the scattering cross-section, or the modulus of the scattering length, is about 60 Bohr radius, which is just fine for thermalization between the two species. Good, what next? Okay, here's a result of cooling a two-species system, and I don't want to go really into details, but we reach with dysprosium T/TF about 0.1 and potassium, and that experiment 0.2 was a little bit at the end of the evaporation stage thermally decoupled, but now we also really reach deeper temperatures for the potassium, actually unmeasurably small temperatures. We rely on dysprosium to measure temperature of our system. Okay, just preparing the initial loading conditions in the traps, we can change the number ratio, but we always have some majority of dysprosium, which, remember, majority heavy is interesting. That's a good choice. Okay, so next slide, ask the question now. The main question is, do we have an interaction control knob? Is there a broad Feshbach resonance for tuning the scattering length? This is an essential question. Without this, we cannot do the experiments. So we started already 3 years ago Feshbach scans and varying the magnetic field here in the region of 50 Gauss and looking at after a whole scan how many particles are lost in the trap. And then you see many narrow things. These ones are the blue ones for dysprosium. These are for potassium. And this is not noise. What you see is already that there are many narrow Feshbach resonances. And there are many narrow interspecies resonances and also intraspecies. No, this is wrong. So this should be interspecies. This is intraspecies, this is interspecies resonance. We see both and many of them, particularly many of them, intraspecies resonances. But this is not unexpected. It's known that dysprosium features many Feshbach resonances, and it comes from the fact that the dipolar interaction mixes in many different partial waves, and this extremely rich Feshbach resonance spectrum. Good, so nature of a broad resonance, but our search was successful, and we found something interesting in the region above 200 Gauss. Can you still hear me? I got the signal that the internet connection is not stable. Everything okay?
Now we can hear you.
Okay, fine, because then I can continue. So I hope there was no interruption. This is a measurement of interspecies thermalization. So we prepare the dysprosium at 1.5 microkelvin. This is not degenerate, it's near degenerate, but still a thermal regime. And the potassium is at higher temperature. Then we hold the system for a couple of 10 milliseconds, typically, or longer, depending on the conditions. And then we see that at certain magnetic fields, here and there in particular, the system thermalizes quickly within a few 10 milliseconds or even faster, and you get equal temperature in this point. So these are points of fast thermalization here, here, and there. So we think that what this is, these are poles of the Feshbach resonance. And we investigated this in much more detail. You can read it in this paper here, and did a lot of thermalization measurements. And now we have a clear picture of the Feshbach resonance scenario. It looks like this. We have a scenario of mainly 3 broader overlapping resonances. in this 200 Gauss region. These are measurements coming from measurements of the cross-section via interspecies thermalization. And then we determined the poles and also zero crossings of the resonances. At the zero crossing, there's no thermalization, which this made us to identify the scenario. And the broadest resonance is here at 217, a little bit more than 217 Gauss. And this is a very broad one and with nice properties for interaction tuning. So we now focus on this resonance. And the first experiment I want to show is some expansion measurements where we can, for example, study this situation near the zero crossing, or here where there's weak interaction, or we can study strong interactions. And now let me show some measurement for some experiment, which is a thermalized mixture, near degenerate. Potassium is a little bit degenerate, but almost thermal. And this is an expansion. So we prepare the cloud in the trap, in the optical trap, and then we turn off the trap immediately, boom, and then the cloud expands. And after 4.5 milliseconds, we take a snapshot, we take an image. And then we see without interaction or with weak interspecies interaction that this is a dysprosium cloud, much smaller than the expanding potassium cloud, and it's clear the mass ratio is 4, so the thermal velocity has a factor of 2. So the potassium cloud should expand 2 times faster, which we see in the experiment. Okay, nothing exciting here, everything easy to understand. But now we do the same experiment, but we jump before we do the expansion, we jump on resonance. We expand on resonance. And then it looks like this. You see there's almost no change in the dysprosium cloud, which is the majority of atoms. But now you see the potassium cloud is much denser. The expansion of the potassium component is much, much slower. It has the size of the dysprosium cloud. So what happens, we sometimes call it a locked hydrodynamic expansion. There are many collisions in the system. And now the potassium atoms cannot freely expand. They experience many collisions with the dysprosium cloud, and the dysprosium cloud slows the expansion down. So they both expand together in kind of what we call a hydrodynamic core. That explains this feature. Okay, so a strong signature of very large elastic collision rate. And now let's look at the profile. If you now look in here, it seems that the potassium cloud is even smaller than the dysprosium cloud, which looks strange. Now we look at the profiles, and there's a surprise. So it is a linear profile, and we see that the potassium component has a central core, and it has side wings, which do not overlap with the dysprosium. It's a bimodality. And when we saw the first signatures of this, we were very excited because bimodality of the minority component is a signature of superfluidity in the mass balance system. You see it in the, for example, in the MIT work on population imbalanced Fermi gases. But wait, superfluidity, really too good to be true? At these temperatures, we don't expect superfluidity. We are too warm. Should be another effect. It took us a while to understand what is going on, but now we do. What happens is it's an effect of the mass ratio. So the lighter component, you can imagine that the lighter component performs kind of a Brownian motion in the hydrodynamic core of the dysprosium cloud, which is confined by the dysprosium cloud and forms a Brownian motion. But sometimes they can escape from this hydrodynamic core, and then they have the faster thermal velocity. Once they escape the core, then they expand more rapidly and form these side wings. And to check this hypothesis, we performed a Monte Carlo simulation, just collision dynamics, resonant collisions, and we see that this explains this generic effect of this mass imbalance system explains the side wings. And this is just an effect based on resonant collisions, but it's specific to a mass imbalance system. In a mass balanced system, you don't have these things. Good, so what next? Let me look again on this picture. Now to analyze it in more detail, we look at the center of the cloud, analyze how many atoms are there, the fraction of atoms in the center, And we see that this fracture of the center really peaks if we tune the interaction. And this is 1 over the scattering length scale. Here, the scattering length diverges, and we see the large fraction, and this decreases then. And our model very nicely reproduces what we see in the experiment. This is kind of understood. Now, the last question is about the collisional stability. Will few body processes kill us? How about the lifetime? And we did lifetime measurements. So this is an experiment where we hold the sample on resonance, here the mixture, dysprosium alone, and you see already the time scale is a few hundred milliseconds or even a second. So there's not a rapid decay. There's some decay, which we still have to understand, but it's relatively weak. And if you just get rate coefficient, 3-body rate coefficients out there in this region, 10 to the minus 25 centimeter per sec to the 6th power over second. And if you compare that, our Fermi-Fermi system with similar Bose-Fermi systems where there's no loss suppression, then you see we have about, with this value and that value for these other systems, we have a suppression which is 2 to 4 orders of magnitude, depending on the particular experimental conditions. So it's nice, the lifetime of the system is long. Now, it seems, where do we stand? It seems we have the key ingredients for experiments in fermionic superfluids we have demonstrated. These are cooling deep into the degenerate regime, interaction tuning via broad Feshbach resonance, and Pauli suppression of losses, enough stability. Looks very nice, seems we are almost there, but the cooling down into the deeply degenerate regime was done at a few hundred milligauss at very low field, whereas the interesting physics happens at high field. And the transfer of the system from low field to high field to do it without losses or crossing many resonances and heating is technically quite challenging. So we're working on that. And the other thing is also the background behavior of dysprosium. And here I want to show just one graph taken on dysprosium alone. So with dysprosium alone, it looks like this. This is a whole scan of dysprosium alone in this high field region. Here's our interesting, the position of the interspecies resonance, but there's no potassium in this graph. Then you see it's a very complicated spectrum. It has a lot of noise, but also some structure, more lossy regions, less lossy regions. The peaks where there's less loss peak, there's more loss. And these narrow peaks, this structure, this is not experimental noise. It's really physics. There are so many unresolved or partially resolved resonances which makes it a little bit difficult. So we have to rely on the experiment on finding the good spots. We located several good spots. For example, here is one, there's one, but it means that experimentally, the control of the magnetic field is a very important thing, and we need a very fast and precise control of a magnetic field. Technical things, but quite challenging. Good, what else? Okay, so last thing. So we were very happy to have a collaboration with a group of Giancarlo Strinati, Camerino, because they are experts in superfluidity and fermionic systems, and they modeled exactly the situation that we have in the trap, exactly our mass ratio, and in a beyond mean field approach, which is when we can expect to give quite accurate results. And so we know for our trap conditions quite well where we expect superfluid conditions. And this is the theory from the Strinati group as a function of the polarization. This is a balanced mixture. This is a majority of dysprosium. Here's a Lifshitz point, and here's the second order phase transition to a superfluid. And I just add some points which correspond to recent experiments we did. And these are here. Okay. So you see, we are not yet where we really expect the superfluidity, but we are quite close. And we work with more dysprosium atoms, and there are several tricks we can play with our trap. Don't want to go into details. Seems that some tricks, improvements with our trap would help. And I'm quite optimistic that with many improvements, we can reach the interesting conditions to be here or below that point, or at the end, reach this Lifshitz point and physics below that. Okay, this is now the end of the second part of the talk. And I just want to show people who haven't performed the work. This is a dysprosium potassium team. Looks quite big, but unfortunately in the last few months, 3 people have left, got new positions somewhere. Happy for them in difficult Corona times, but the team is now, we have to rebuild the team and have open positions on this experiment. So there's exciting physics ahead, and let me just with the last slide give a very general conclusion. And this is, I hope I could convince you that ultra-cold fermion systems mixtures are exciting. They are a great playground for physics of strongly interacting many-body systems, and there are many opportunities and challenges for experiment and theory ahead of us. And with that, I would like to thank you for your attention.
Thank you very much. I don't see any question in the chat box. So I have a question. Dysprosium is a dipolar system.
Yes.
So it has a strong interparticle interactions, long range. And when you mix with lithium-6, do you expect polarization-induced other kinds of interactions apart from S-wave interactions?
I mean, there is, of course, a strong mixing of higher partial waves, but we are now at the moment focused on the S-wave interaction. And the higher partial waves give rise to these narrow features which intrinsically lead to loss. We have also some experiments to understand it. But I mean, the dipolar character certainly has some effects. But the dipolar interaction, if you compare it with the Fermi energy scale, is still not very large. So it's an effect that you can see some maybe 10–20% effect depending on the conditions. So you see some slight elliptic deformation of the system, some ellipticity effects and so on. It's not very strong. But it could be interesting in the future because also the Fermi surfaces are deformed. And if you match the Fermi surface from one direction, you may get a mismatch in the other direction. And that could also lead to interesting new phases.
So in the phase diagram, you showed a superconducting phase and also other phases, a Sharma phase. So can you please elaborate a little bit about the different phases in spin imbalanced or mass imbalanced systems?
Okay, so this is,
Yes.
This is actually, I have to admit, this feature in the phase diagram, it's not there in other calculations. I have never completely understood what that means here. So there's it's somehow a partially filled gap of the system, but I cannot say anything more about this here. This is we focused on this region, and also even the Sama phases are predicted somehow for the mass balance system, but to my best knowledge have never been clearly observed. If you have an idea, or if somebody has an idea in the audience, let me know.
So it is predicted that in the case of spin imbalanced or mass imbalanced superfluidity, one can have gapless superconductivity.
Yeah.
But as you said, that it is yet to be realized with cold atoms, and
I think there's at least, it's a fair statement today, there's no clear experimental observation of these gapless. So of course, there are experiments which are consistent with that, but not yet a clear observation. It surprised me actually many times. It appears in the literature quite often, but there's no really dedicated experiment exploring these possible Sama phase. Maybe it's hard to see it in the experiments. We need a clear detection tool. So what really distinguishes the Sama phase from the other phases? So we have to prove superfluidity, but show that the gap is kind of partially filled or even gapless. It would be maybe a combination of methods to detect superfluidity and radio frequency spectra, for example.
Sourav, do you like to make any comment? My co-organizer.
No, I'm fine. Thank you. It's a very nice talk. So one thing, so is this potassium dysprosium somehow the best candidate that you could choose from the periodic table, or this just happens to be convenient?
I mean, there are several, let me check this one. There are several different criteria what you want to have. First of all, you want to have a mass ratio which is still sizable, but not too large. If it's too large, then in the Fermi-Fermi system, you can get Yefimov states, and this makes the system more complicated and unstable. Could be another interesting direction. I mean, combining dysprosium with lithium-6 could be extremely interesting, but the physics will be even more complex because of these three-body states. It's also interesting for the future. So you want to have a mass ratio. You want to have at least the prospect of Feshbach resonances. So we know if you combine closed shell group 2 atoms, strontium or ytterbium, with another species, it will produce only narrow, super narrow resonances. And what else? Then it's also, I mean, from the experimental point of view, you want to have something which is relatively easy to prepare. And potassium at 40 and also dysprosium, actually dysprosium is a very nice species for cooling experiments. The Doppler cooling with a narrow line works extremely well, and you can prepare it well, and they are compatible. So the optical potentials are similar. They mix very nicely. This is all very nice. And from all these points, I mean, there's not so much remaining. I think the lithium chromium system is interesting. We're pursuing this in Florence. The potassium dysprosium system, also the potassium erbium system could have interesting properties. But that's my favorite three combination, and we picked the dysprosium potassium.
Okay.
Okay, so if there is no more question, let us thank the speaker for a very interesting and quite illuminating talk. This and I'm sure that this will bring new directions in the research with ultracold fermionic systems. So with this, we close this session. Thank you very much for your attention.
Yeah, so thanks for your attention. It was a great pleasure.
Thank you. Yeah.
Thank you very much.
So Dilip will take over now.
Yes, Dilip.
Okay.
Hello.
Okay.
Great.
Hi.
So
Hi. Okay. So hi. Good afternoon, everybody. So in this session, we have three talks. The first is by Subhasis Sinha, second by Sebastian Wuster, and the third by Manas Mukherjee. So our first speaker is Subhasis Sinha. Hi, Subhasis. Can you come? Can you activate your video? Hi, Subhasis.
Hello, sorry, I was not.
Okay,
I have to
fine.
unmute this. Now you can hear me.
Okay.
I guess.
Yeah. Yes.
Yeah. So first of all, I apologize that my connection, internet connection, is not very stable. So
okay.
I may get disconnected sometimes. So please tell me that time if there is some problem in.
Absolutely. And I have one question for you, Subhasis. Yeah. So would you like to take questions during the presentation or at the end of your presentation?
Whatever. I think end of the presentation is also okay. But okay, let me. Can I share the thing? Is it?
Yeah, sure. So then let me give a brief introduction before you start. Will that be okay?
Okay, sure.
Yeah. So Subhasis Sinha is from IACS, Kolkata. So he did his PhD from Institute of Math Science, and after that he has held various positions at various places of renown. And his interest is on ultracold atoms with a perspective from condensed matter physics. And in recent times, he has been working on these quantum scares. And today he will be talking to us on chaos and quantum scares in Bose-Josephson junction, coupled to a bosonic mode, a topic that's of great interest considering the use of these finite size quantum systems in quantum information. So Subhasis, over to you. So anyone can ask a question either through the chat box or by unmuting yourself. So Subhasis is willing to take questions during the talk as well. So Subhasis, over to you.
So sorry. Okay. So is it visible now? The slide is the slide
Yes,
visible?
it is visible. It is visible.
Okay. So thanks, Dilip, for this nice introduction, and I also thank the organizers for giving me the opportunity to present this work. So today I'm mainly talking about the quantum scarring and chaos in Bose-Josephson junction coupled to a bosonic mode. So the outline is the following. So first, I'll just briefly discuss about the ergodicity in the quantum system, closed quantum system, and next I'll just go to the Bose-Josephson junction coupled to the bosonic mode to discuss the chaos and ergodic behavior and scarring phenomena. And all the meaning, since this conference is basically on the cold atom, so that's why I choose this topic, that's a Bose-Josephson junction. But the scarring phenomena can be seen in the other systems also, but there's another system which is also interesting in the context of cold atom, which is a kit top. So I just briefly discuss, although this is not the main focus of the present talk, but still if time permits, I'll just discuss about the scarring in kit top model, and then I'll summarize it. So this non-equilibrium dynamics and ergodic behavior of isolated quantum many-body system has become an interesting topic in recent years, particularly because of lots of ongoing experiments on cold atom, because cold atom system, particularly in the optical lattice or the strongly correlated systems in the optical lattice, has become a test bed for studying such non-equilibrium phenomena. And also this ergodicity, and ergodicity is basically a pillar for statistical mechanics, which we generally study in the undergraduate level, but its root or how it's originate in the quantum mechanics is not very clear, because in classical system it is quite clear that there is a this ergodicity arises from the phase space mixing of the this chaotic trajectories, which is basically triggered by some chaos, etc. And but such type of mechanism is absent in an isolated quantum system, since there is no such description of phase space or phase space trajectories because of the uncertainty principle. And so that to explain the thermalization in an isolated quantum system, there's an eigenstate thermalization hypothesis has been put forward, which proposes some type of thermalization for each eigenstates. But and it has a close resemblance with the random matrix theory. Also, if the quantum system shows a signature of chaos in the quantum system, can also understood from the random matrix theory. So in this context, the random matrix theory plays a very important role to understanding the ergodic behavior of the quantum system. However, it is not very clear that which quantum system will thermalize and which will be the degree of ergodicity of different quantum systems will be quite different. So there are different factors which hinders the thermalization, and also the violation leads to the violation of eigenstate thermalization hypothesis. So one is of course the integrable systems, because there are lots of conserved quantities, and that hinders that is generic belief is of course that this will not thermalize the integrable system, rather non-integrable models are better for thermalization. But there's a very interesting example which is found in the recent year, which has become very popular in recent years, that is the many body localized system, where not only the ground state, even the excited state of the systems remains localized, and it is hindering the thermalization of the system. So there are also certain systems has shown the non-ergodic phases, where the system has some sort of states which are in between, which is intermediate between the localized states and the plane wave like extended states. So they are neither completely localized nor completely extended. They are called the multifractal states. So presence of the multifractal states make the quantum system very interesting. They show some sort of anomalous thermalization, etc. And recently it has been also found out that there are certain specific type of initial states that also shows in the non-equilibrium quantum dynamics a athermal behavior, so which never relax to the thermal states. So these are called these are attributed to many body quantum scars. So I'll mainly focus on this phenomena of quantum many body scar in this talk. Okay. So like one example of this localized phase of this quantum system can be achieved by this quasi-periodic lattice. So quasi-periodic lattice is created by these types of potential where beta, this parameter beta, is considered to be a irrational term, typically some sort of Diophantine number or golden ratio, etc. And this model, in case of a nearest neighbor hopping term, this model is known as the Andrew-Aubry model, and it shows a localization transition. And even with different many body localized states, even the localization of light, etc., has been realized in this creating this quasi-periodic lattice. So this is very common in the present in recent years. So we have studied this thing with a long range interaction, not long range hopping term, not a just a nearest neighbor hopping, but long range hopping. And this gives rise to the non-ergodic phases, not only localized, but the non-ergodic phases, depending on the power of this hopping term. So if A is less than 1, then one can say these types of non-ergodic phases also. Also, there is a possibility to see a simple system, very simple system, like a driven spin, but driven in the quasi-periodic manner, so that there is some sort of sequence like the Fibonacci sequence. The spin is driven by the or kicked by the Fibonacci sequence. In that system, it shows that the phase space trajectories shows quite a chaotic behavior, irregular behavior, but the Lyapunov exponent vanishes. So this is a very strange system, and a closer analysis also reveals that there's some sort of fractal behavior of this dynamics of the spin, and also the evolution operator. If one study the eigenvalue, the eigen properties of the eigenvectors, it shows the multifractal nature. And in presence of interaction, this also undergoes from the non-ergodic phases to the ergodic transitions. It's possible. And in a recent experiment, this many-body quantum scarring phenomena has been observed, where there's in a chain of Rydberg atom experiment is done on a chain of Rydberg atom. And if one starts with some special initial states like a charge density wave-like state, so this is the initial state, it turns out that these types of particular, some special initial states do not relax or do not thermalize. It ultimately shows some sort of a revival phenomena like this. There's some oscillatory or revival phenomena, and it does not thermalize, unlike other states which are very in this strongly interacting system. Many other states also thermalize, but except a few. And this is clearly the violating the ergodic evolution. So typically in the ergodic evolution, we expect that it should be a Markovian nature will be there, so the memory will be lost ultimately. But there is a memory effect will be still retained in such thing, and that's why there's a revival phenomena is there in this scarring phenomena in many body system. But originally the quantum scar was proposed for a non-interacting chaotic system, and like the chaotic billiards, where the analyzing the eigenstate shows that there's a reminiscence of the unstable periodic orbits. So orbits are unstable, they're not really existent, but still their reminiscence can be found in the wave function. So that was termed as the quantum scars. So what is the connection between the underlying unstable dynamics and this many body quantum scar, which just violating this ergodic behavior or violating the ETH hypothesis, etc. So what the connection is not very clear, that what is the underlying unstable dynamics behind such formation of the many bodies car. But if one start to answer this question, I think it is better to study some sort of collective models which shows the underlying connection. So in that context, I will consider a model which is already studied in the cold atom system, which is the Bose-Josephson junction. So this experiment has done long back. And this Josephson junction is created by loading the condensate in the double well trap. And this is the some effective Hamiltonian describing this model within the single mode approximation. So first term represents the tunneling between the tunneling of particle between these two well in the left and right well. And the second term is the interaction, the on-site interaction of this. So this is like the Bose-Hubbard dimer, a simple model. And this model has been analyzed semi-classically, and the different type of dynamical branches of this oscillation has been studied in this work. There is a nice theoretical work, and also lots of experimental work has been done where there's a very interesting phases are observed. So there are three different types of oscillatory modes can be observed in the Josephson junction. So first of all, there are two collective variable in this case. One is the number imbalance, the number difference between left and right well, and the relative phase between them. So this model can also be described in terms of a large spin system. So I'm not considering this thing, but effectively in terms of these collective variables z and phi, the classical Hamiltonian can be written in this form. Okay. And analyzing the equation of motion of this classical Hamiltonian, one can find out the steady states and the oscillations around such steady states. So first type of oscillation is the typical AC Josephson oscillation, which occurs around the zero number imbalance and when the phase difference is zero. So that the frequency of this oscillation is this, and it is always stable for all parameters. There is another interesting branch of oscillation can be seen, which is called the pi mode or pi oscillation, where the imbalance is still zero, but the relative phase is pi in that case. And the oscillation frequency looks like that. And so it is very clear that this becomes unstable. This pi oscillation becomes unstable when coupling constant exceeds this value J. And there is another self-trapped regime which occurs in the strong interacting regime when U is very larger compared to this J, and there is a spontaneous imbalance will be formed in this system. So in this picture, this is a theory and experimental work, and there are these two types of oscillation. The AC Josephson junction, that Josephson oscillation is shown by these blue lines, and this red colored thing are the pi oscillation, pi modes. This can be seen. So in this work, I'll mainly focus on this pi oscillation. So this is the main focus of this present work. So this is just a simple isolated Bose-Josephson junction, and there these types of mode, this pi oscillation can exist and which can become unstable in some parameter regime. Now, second question one can ask that it's interesting to see that study these types of dynamics in presence of the dissipative environment. So the dissipative environment can be generated by this coupling this Bose-Josephson junction with some type of phononic bath, which can be created by coupling it to some two condensates in the left and right, so that the Bogoliubov modes can couple to this left and right side of this Josephson junction, and this will act like a bunch of oscillators coupled to the Josephson junction, like a Caldera-Leggett model, which gives rise to the dissipative effect in the Josephson. We studied the fate of the different types of pi mode and the imbalance state, this self-trapped state, etc., in presence of dissipation in this work. But this is the in this case, of course, when you consider a bath or a dissipative dynamics, there that different many modes are important. So there are many k modes, like the Bogoliubov modes are present in this case, they are coupled. But we are considering a simple case when there is only one bosonic mode is coupled to the Josephson effect and what happens to the system. So this can be achieved maybe coupling the Josephson junction with some cavity mode, and we can, this is described by this Hamiltonian like this, and this can be written in terms of spin Hamiltonian with a very large magnitude, where S is n by 2, n is the number of particle. And in the spin language, this Hamiltonian can be written in this form. So Sx term gives this tunneling between left and right well of the Josephson junction. Sz square gives this interaction term. And then there is a Sz with a B plus B dagger that gives the coupling with the bosonic mode and the Josephson junction. And omega 0 gives the mode frequency of this. So the effective...
Hi, Subhasis. There is a question in the chat box. So the question is, can you please tell once again what is quantum scar?
Okay, so well, so this is the original work of Eric Heller, where the quantum scar has been proposed. So in the chaotic system, studying the chaotic system, the wave function of the chaotic systems shows that reveals the some reminiscence of the unstable trajectories. So here, if you consider, it's a non-interacting system, just but because of the geometry, the system shows chaos. So classically, if you consider the different trajectories, this becomes chaotic because of this bouncing, and this trajectories become chaotic and completely filled up. So the reminiscence of these unstable trajectories is called the scar, typical, the quantum scar. But the many body quantum scar, which has been observed in the recent experiment, these are like some initial very complicated many body states which gives rise to athermal behavior, particularly the revival phenomena, and violating the sort of ergodic behavior or the ergodic dynamics. That is the many body quantum scar, which is called in the present experimental context. Okay. Is it clear, or any question?
Yeah, it's
If
fine.
there,
Yeah.
okay, if there is any question, please unmute your speaker and please talk to me. Okay. And okay, so yeah, so this is the Hamiltonian. We are considering the Bose-Josephson junction coupled to a one bosonic mode, and the semi-classical description of the system can be written in terms of the coherent states, which are the one is the spin coherent state, and another is the bosonic sector. We can consider the bosonic coherent state, and within that prescription, one can obtain the classical version of this Hamiltonian, and where P and Q are basically the bosonic mode can be written as a classical harmonic oscillator with coordinate P and coordinate Q and momentum P, and the equation of motion, etc. This can be analyzed. So this work is actually done with my student Sinha. So, and the interesting thing is that this model, although the isolated Bose-Josephson junction does not show any type of quantum transition, but when it is coupled to the external bosonic mode, it is somewhat similar to the decay model. And it shows a decay-like transition, a quantum transition in this model. So there is some critical coupling strength, gamma C, above which the system will show a spontaneous imbalance will be generated in this system. And that's a quantum phase transition, which can be detected by calculating the different quantities, physical quantities like Sz, etc., spin component, or even the entanglement entropy of the ground state that shows a peak at this transition point, etc. And the energetics in that, the energy level, the etc., can be shown in this figure. So this figure actually shows the variation of the ground state with the coupling with the bosonic mode. So where there is a kink-like structure is there, that is the point where the quantum phase transition occurs, and then the ground state actually shows a symmetry broken structure, etc. And here the color scale plot shows the ergodic properties of the eigenstate from the entanglement entropy. So we calculate the degree of ergodicity of eigenstates from a relative entanglement entropy. Calculate the entanglement entropy by just integrating out the bosonic modes, and then find out the maximum entanglement entropy in that case, that is for spin system of large spin, which is log 2s plus 1. So we find out the relative entanglement entropy behavior. That is very clear that near the ground state, the states are not very ergodic. Degree of ergodicity is less, but as you go to the higher energy states, this will become ergodic. And above the quantum phase transition, there are three steady states can be there. One is the symmetry broken steady state, which is basically the ground state drawn by this red color thing. That's the thing that is symmetry broken steady state. Then there is a symmetry unbroken and unstable steady state. So a phase transition can be viewed as just a bifurcation, simple pitchfork bifurcation type, and so that symmetry unbroken branch will be always unstable after the phase transition, and that's denoted by this dotted line at energy density EC. And moreover, there is another steady state is present which corresponds to the pi oscillation of this mode of the Josephson junction. That's is denoted by this E0. So you see that the pi oscillation, pi mode can still exist above the quantum phase transition and well inside the state regime where the states are quite ergodic, quite large entanglement entropy. Okay. And we will see that effect of this pi oscillation in in this regime. That is the main objective of this
Hello.
work. It also, hello, yes.
Sir, why the energy, and is it negative energy? -1 EC.
It is indeed negative energy density. In fact, this is not the energy divided by s, the magnitude of the spin is called. So yeah, it can be negative. Yeah.
Okay.
Okay, there is also another interesting transition that occurs in this system, which is called the excited state quantum phase transition. This occurs at this energy density EC corresponding to the symmetry unbroken state. Basically, it separates the states in the two parts. So the below this line, this EC, the states have some sort of symmetry broken nature, and above this line, the state shows some symmetry unbroken nature of this. So anyway, this is not very important in this context of scarring, but it is an interesting phenomenon. And also we study the classical dynamics of this. We just analyze the fixed point structures, etc., but we can do the full dynamics of this system and calculate the phase space structure. It shows that after the quantum phase transition, there are this phase space shows a very chaotic, very irregular type of behavior. Although there are this symmetry unbroken, meaning symmetry broken phases after quantum transition, these are quite visible. They show regular regime, but this regular region in the phase portrait that shrinks, and there's a field with the irregular trajectory. So it's just classically it indicates the chaotic behavior. Also from the entanglement entropy of the energy eigenstate, we have seen that there's a very states become ergodic as you go away from the, above the quantum transition, and higher energy states becomes more ergodic in that sense. So we study the level spacing, the spectral statistics of this system. It shows that above the quantum, meaning below the quantum transition, it shows a regular behavior, and regular behavior meaning is a level spacing distribution, is a Poisson statistics. It is according to the Barry-Tabor's theorem, or conjecture rather, that regular behavior is demonstrated by the Poissonian statistics. And the BGS conjecture says that the Wigner-Dyson statistics can be observed in the chaotic regime. So where we can see the classical chaotic behavior, if we analyze the spectral statistics, it will reveal these types of Wigner-Dyson type behavior. That's also we observed. And there's another parameter, it's called the ratio of level spacing ratio of levels, consecutive level spacing. And if we calculate the average value of this quantity, this also shows a transition from Poisson to GOE around this quantum transition. So in this regime, the system becomes chaotic. It is expected. So it's become more ergodic and chaotic. But as we have seen from this figure, that although the system is showing ergodic behavior, but there is still this pi oscillation state still persist in this regime, in the ergodic regime. So what is the effect of this pi state here? So if we calculate the frequency of the pi oscillation, it shows this behavior. This is the frequency analytically one can find out, and it turns out that this becomes unstable above this critical coupling strength gamma u is given by that, and this instability value that can be tuned by tuning the frequency of this mode omega 0 that very much. So if I fix the gamma value and just tune this frequency of the mode, we can get the regime where the pi mode is stable or it can become unstable. So if we consider the regime when this pi mode is unstable, then we see the phase space or the Poincare map is called. So that shows at this energy, the energy of this pi mode, it shows a very chaotic behavior. Whereas when this pi mode is stable, then it shows a mixed phase space like behavior when there is a stable region around the pi oscillation. Also, the entanglement entropy shows when this pi mode is stable, then it shows a dip in the entanglement entropy around this energy density 1, where this pi mode occurs. And if the pi mode becomes unstable, then of course the entanglement entropy just increases without such dip. So we also calculated this level spacing ratio, average of the level spacing ratio. It shows the very clear effect of this stable pi mode, the presence of stable pi mode. It reduces the chaotic degree, and when the pi mode becomes unstable, then it increases the chaoticity or R average that shows these things. Also, the entanglement entropy shows the dip in the entanglement entropy shows the opposite behavior, of course. So there is a clear effect of the underlying dynamical steady states on the ergodic behavior of a quantum system, it shows. Next question one can address, what happens when the pi mode become unstable? Can we see the signature of this unstable pi mode? The answer is yes, we can see some signature. So if we calculate the Shannon entropy instead of the entanglement entropy, if we calculate the Shannon entropy of these states when the pi mode become unstable in the chaotic regime, we see this behavior. So most of the states, the Shannon entropy forms a band-like structure. However, at this particular energy E is equal to 1, the pi mode forms. So around E is equal to 1, we just studied the structure of the Shannon entropy of the states. But there are certain states which shows a strong deviation. And we just picked up certain these states which shows the strong deviation of the Shannon entropy and analyze these states. So we calculate the phase space, semi-classical phase space distribution or the Husserl distribution of these states, and these are shown in this figure. They clearly shows that there's a high density, phase space density around this pi value. So these are like the reminiscence of this unstable pi mode. Also, certain states shows the oscillation, an orbit around this pi oscillation. So these are like the clear signature of the scars in this system, in the states. Also, we can describe this type of unstable steady states by this coherent state structure, which is called as pi, which we call pi, which is just the coherent state, product coherent state. And then we choose this type of this eigenstate and take the overlap with this pi state, semi-classical pi state, semi-classically describing this pi mode fixed points. And then we find that these states which are deviated very, which has a Shannon entropy is deviated from this limit, they show a very strong overlap with semi-classical pi states. And this is a one signature of this scarring phenomena. And also we find that the degree of scarring, what I mean by the degree of scarring is that if you see this phase space density, and if you here you see the strong localized structure, but the localized structure will become faint later, but as you increase the instability of the system. So by increasing the coupling strength, then one can find this, the instability of this unstable pi mode will increase, and that will show that the visibility will also decrease with that, and also the overlap factor that will decrease. So that will give the degree of scarring in this system. So okay, and another interesting point is that the states, the scarred state that violate Berry's conjecture. So typically Berry's conjecture says in the ergodic states that all the amplitude of the states, they follow a Gaussian probability distribution, or in other words, they have some sort of things called, in the random matrix context, is called the Potter-Thomas distribution. But we found out there is a strong deviation from this Potter-Thomas distribution for these scarred states. So Berry's conjecture is violated for these states carrying the scars. And also the survival probability, the dynamical signature of the scar states can be found from the survival probability. If we start with this coherent state corresponding to this pi state and see the time evolution, then we see the very short time scale, we see this type of oscillatory behavior, type of revival and oscillatory phenomena in this case. And then in the long time, it is deviating from the random matrix prediction of the survival probability. So there is some random matrix prediction of this survival probability in long time, and it shows a deviation from this. But whereas if you just consider the same energy density, some arbitrary initial states, initial coherent state that show very rapid decay of the survival probability and converges to the random matrix prediction. And another observable effect of this scarred state is the phase coherence. So so far we are considering the relative phase as a classical variable, but actually this is a quantum state. So this is a phase, states can be defined in this way, and one can calculate the phase fluctuation in this Josephson dynamics. So phase fluctuation, the better way to calculate is that cos phi average. And if we calculate for this pi oscillation states, when the pi state is of course unstable, but still we see that the this cos phi average, this thing that shows a phase coherent structure, whereas other state that shows a decay to zero, that phase phi. So that shows a phase diffusion phenomena in that sense. For any ergodic or random states, it shows a phase diffusion. Moreover, after the evolution of this pi state and for any other random coherent state with the same energy density, we find the two different structure. In this case, after the time evolution, we still see there is a accumulation of density around this pi point, whereas a random state show a very random density, phase space density. In that case, there is a clear deviation from this. So this is a very nice experimental, can be experimental signature for studying the scarred states. Okay, so this is the first part of this Bose-Josephson junction, etc. But similar phenomena can also be studied.
Hi, Subhasis, you have 10 minutes.
Okay, so I'll just finish it then. Okay, so another example is a kick-top model. In fact, this kick-top is this described by this Hamiltonian. It has been studied in the context of quantum chaos and has been realized in the cold atom experiments like these chromium atoms. And although the spin is not very large in this case, and also this has been realized in the superconducting qubit. So where there is a one part is the SX, and there is a periodic kicking term is described by this. There's a periodically the spin is kicked with a time interval t, and the mu represents the kicking strength of this. So this system we have actually this model we analyzed is described in this paper with my student Devabrata Mandal and Sudip Sinha. So that was a different model. We considered basically a coupled top, a kicked coupled top model, but in some limit it turns out to be the exactly same as the kick top model. And since kick top has been observed in or realized in this cold atom experiment. That's why I'm just focusing on only this part, the scarring in the Kirchhoff model. So there also we can derive the classical equation of motion in the limit of large S limit, and this gives rise to this type of a classical map. Basically, the stroboscopic evolution can be written in terms of the classical map, where n is the nth kicking in that way. And analyzing this map again, we calculate find out some of the fixed point and steady state, and the full dynamics shows this behavior. So initially there is a very nice fixed point, a very regular trajectories, and then there is a bifurcation of the one steady state that occurs. So one steady state becomes unstable, and then it bifurcates with this, and then again different type of states are forming with increasing kicking strength. And it is very interesting. In the intermediate regime, it shows a mixed phase space regime. In fact, the mixed phase space regime is a very interesting, shows interesting behavior, because that shows a local ergodic behavior in the system. So certain regime is regular and certain regime are chaotic. That's very interesting. And also the quantum scar, this is the regime where one can find out the significant effect of the quantum scars. And later, of course, with a large kicking strength, this becomes completely chaotic. So we analyze this unstable fixed points or unstable steady state, and also the unstable two cycles. So two cycle is like a smallest periodic orbit that also observed in this case. So similar way, we have seen that in the basically this is a dynamical system, unlike the first Bose-Josephson junction. Here is a time dependent problem. So we analyzed it the Fluke method, and we consider the Fluke eigenstates here. So we find out the Fluke eigenstates which carry the scars of these types of unstable fixed point from the overlap of the semi-classical description of these fixed points. And this really show the Husserl distribution, so the clear signature of this trivial fixed point, and then there's a symmetry broken or the non-trivial fixed point, etc. All these cases. And also the survival probability, corresponding survival probability show the oscillatory behavior in that case. And interestingly, in this case, we have also found out the scars of the unstable two cycles. That behavior is very interesting. Some figure is not there, but it shows a very interesting dynamical revival, meaning type of a revival phenomena in the two particular points. So this is has a very interesting phenomena. Also, this scarring phenomena can be detected by this using the fidelity out of time ordered correlators. So out of time ordered correlators, or OTOC, has been very recently developed to understand the chaos in a quantum system which has some exponential in time behavior, and this exponent gives some analog of the Lyapunov exponent. But there is certain generalization which is called the fidelity OTOC. And fidelity OTOC, the advantage is that this OTOC will reduce to the fluctuation of these operators. So if we consider the total spin as a operator, as a given operator, then the spin fluctuation will be basically proportional to the OTOC of this. And it shows a very nice oscillatory behavior. The scar state shows a very nice oscillatory behaviors, or very slow growth, particularly the two cycles, they show a very slow growth compared to the ergodic states. And this can be used to detect the signature of this scarring. So that local behavior of this ergodic behavior can be understood. This is a from this mixed phase structure. So in this side, left side, we have just shown the classical phase portrait of some model. And here is a right hand side. This is basically the entanglement entropy and survival probability. So this fingerprint of this dynamical behavior can be still observed in the entanglement entropy or the survival probability, which actually quantify the degree of ergodicity in the systems. So there is a clear dynamical route to ergodic behavior in such system can be understood in that way. Also the quantum scarring phenomena can be understood. So this unstable, so this understanding this connection between the unstable dynamics and quantum scarring phenomena, I think the collective models plays a very important role. And also it will be interesting to investigate the higher energy collective states of the many body systems. and OTOC or FOTOC can be used to study the dynamical signature of quantum scars. So thank you for your attention and effect.
Hi, Subhasis. Thank you for a very good presentation. Now we have time for 2 or 3 questions. So anyone, you can either unmute yourself or you can type in the chat box.
Yeah, I would prefer if you just ask directly. You can unmute and ask directly. That will be better for me so that I can go back and forth to the slides and answer.
Looks like there are no questions. So I have just one sort of curiosity, Subhasis. So you were mentioning that this quantum scarce, it is sort of, in the case of a single particle, there is a sort of a direct comparison with the classical system. But in the case of quantum many-body scale, is there some sort of a classical counterpart to that?
Yeah, that was the question, that what is the classical counterpart for the many-body system. So this is not very clear, but if you consider this interacting system, like of course, if you consider the Josephson junction, for example, of course, it is a many-body and interacting system. However, since there is a collective description is possible in such system, in the large n limit, one can write down the classical equation, etc., so that the correspondence can be understood very clearly. Okay. But there is a recent work to understand this classical thing from the matrix product states. So if one start with some type of a product ansatz of this matrix, meaning not well, some type of a ansatz of the matrix product state, and try to get a corresponding equation from the variational dynamics, then it also can show type of a very interesting mixed phase space behavior that was recently observed in cases, but not every cases it is very clear, because the mechanism behind this many body scarring, still there is some sort of an emergent symmetry is turns out to be a basic mechanism. So there is certain state turns out to be very protected, symmetry protected state, and which does not mix with the other chaotic state, so that if you start with a mixture of those particular states, then they will just show a revival kind of phenomena rather than a decay or thermalization, etc. So that was the mechanism.
Okay. So if there are any other questions, then we can thank Subhasis for a very nice talk, giving us a very good account of the quantum scar states. Okay, thank you, Subhasis.
Okay, thank you.
Okay, hi, Sebastian. So our next speaker is Sebastian.
Hello.
Mr. Hi. So okay, so you're online. So
yes.
Hi. So yeah, so let me just give a very brief introduction. So, because since this being online, since there are no physical interactions, probably it's good to give a very short introduction. So Sebastian Wuster did a PhD from University of Queensland. After that, he has held various positions at various renowned institutes. And since 2016, he has been at IISER Bhopal. He has done exceptional work in the Rydberg atoms in the context of BEC, that is ultra-cold quantum gases. And today he will be telling us something about Rydberg atoms in different environments. So the title of the talk he shall be giving is Rydberg atoms in Bose-Einstein condensed environments, from bubble chambers to controllable open quantum systems. So Sebastian. And okay, one question I have.
Thank you very much.
Sebastian, I have one question. Would you like to take questions during the presentations, or would you like to have it? Okay. So then,
I'm just confused. Yeah, I mean, I'm very happy to be interrupted. If anything is unclear what I say, please ask. Can someone quickly help me how I enable my mouse cursor? That I kind of
okay.
Up here somewhere.
Okay. Now,
can you see my screen?
yes, it is visible.
Okay, well, unfortunately not the mouse cursor. Okay, fine. Let me go without. So yeah, thanks Dilip for the kind introduction. So in this talk, essentially, I'll try to convince everyone that it's a very exciting plan to excite a Rydberg atom within a Bose-Einstein condensate, something that is actually being done in present experiments. The overall topic, of course, fits into the study of impurities or quantum impurities, where we're all probably used to the fact, like shown in the cartoon on the top, that if you have a sort of well understood and regular bulk structure, such like that condensed matter crystal, and now you're putting some minority or impurity species into there, that even though maybe there's not a lot of those, the whole fact that they break the regularity of the bulk structure gives rise to interesting qualitatively new features. And this is recently an expanding area also in cold atomic physics, where we've probably seen many other lectures and talks in this workshop, or will still see, where people put impurities such as ions, other types of atoms or molecules into ultracold gases or BECs. Right? And then one can use these hybrid systems to do fundamental studies of, say, interactions between the ions and the atoms, or formation of new quasi-particles such as polarons. Or in the case of molecules, there would be additional degrees of freedom, such like the rotation of the molecule, that I might be interested to learn. Right, so in this talk, I'll focus exclusively on the combination of putting a Rydberg excited atom into a Bose-Einstein condensate. To start off with putting everyone on the same page regarding these two, right? So if you have your hydrogen type of single valence electron atom, we're used to describe that with these three fundamental quantum numbers, N, L, M, where L and M are for angular momentum and N is the principal quantum number. In the ground state, your hydrogen atom is of the size of the Bohr radius, but we know that the orbital radius of the electron scales like the principal quantum number squared. So as we are increasing the principal quantum number, that atom becomes big rather quickly. Right, and then if we keep going that way, already at the principal quantum number 20, that atom is larger than several biomolecules or smaller biomolecules, or here of the size of that carbon nanotube. And at n equal 100, the electron orbital radius of a Rydberg atom is larger than a virus or comparable to an optical wavelength. But they are, of course, very extreme atoms as such. And because of this extreme distance between the electron and the nucleus, you also get extreme properties such as very large electric dipole moments or transition dipole moments. The atoms become somewhat fragile, so therefore it's natural for many experiments to excite these in an ultra cold setting, where the coldest of those we can think of is, of course, a Bose-Einstein condensate. Right, so there on the left, I'm showing that in famous cartoon where you cool down the classical billiard ball atoms more and more towards the critical temperature, where their de Broglie waves then begin to overlap until the bottommost frame, where all these atoms have gone into one giant matter wave. From the theoretical point of view, this is nice because now I can replace the nasty many-body wave function that has a coordinate for each of those maybe 100,000 atoms by just one wave function phi of r there in the top right. That is the mean field wave function that now describes all the atoms, right? So that is that red line that is in my bottom left plot, right? So all the atoms share that one wave function. In another viewpoint, I can say I replace my field operator with that one mean field wave function. Just one quick question, sorry, when I share screen, you only see my screen, you don't see that sort of participant menu that is clogging up the view on my local screen, is that correct?
Yes, that's right.
Okay, right, so if we do this theoretical simplification that we say all the atoms share just that one wave function phi of r, we can describe the BEC with that well-known Gauss-Pitaevsky equation that really very much looks like Schrödinger's equation, except that U0 mod phi squared term that is proportional to the density of the Bose-Einstein condensate and has to do with atomic interactions. Right? So the atoms can kick each other. Luckily, this quantum scattering process is also very simple at these very cold temperatures. And because of the S-wave scattering approximation, we can get away with that simple nonlinear contact interaction term. Right, so in the end, we have a three-dimensional wave function for maybe 100,000 atoms, which is much, much nicer than 3 to the n. Something else we will use is I have this one complex wave function that really describes a very large number of atoms, and that is fully phase coherent. So I can attribute a complex number at every point in space. Now I put these two together and excite, so there are experiments that actually have excited atoms to these very high-lying Rydberg states inside of a Bose-Einstein condensate. So in some sense, you're having extreme atoms in an extreme environment. What I'll try to convince you in the remainder of the talk is, despite these extreme properties or scenarios, I can have a relatively well-controlled system where maybe for the Rydberg atom, I can get away with looking at a couple of different electronic states, such as the S and the P angular momentum state, right? So no angular momentum, one angular momentum. The Bose-Einstein condensate is also very nice because either it's just the mean field there on the left, like the phi of X term, or at most I can add a sum over all sorts of phonon excitations, right? So quantum sound waves, if you so want, that I also believe I understand relatively well. Then there's a very interesting and also controllable interaction between the Rydberg atom and the Bose-Einstein condensate that the blue line I'll explain you on the next slide. And I just want to flash here because there's no chance later, right? So we can also engineer some well-controlled long-range interactions through dressing techniques. And everything I say in the following would be possible with those also. I'll try to actually cover 3 topics. Don't be afraid, they're all topically related. So I think we can manage to do that. Right, so the first one will be tracking mobile Rydberg atoms in the Bose-Einstein condensate. So that means we have a bunch of Rydberg atoms that are shown as blue balls that are in the same electronic state, an S state, and they're moving. In the second topic, we rather don't allow them to move, or we assume times are too short for them to move, and we excite them all in about the same place, multiple excitations. And in the last topic, I'll be allowing 2 electronic states, an S state and a P state. One amazing feature of this platform is that once you excite a very high principal contour number state inside the Bose-Einstein condensate, you can easily and typically are in a scenario where there is many green ground state atoms in the right-hand side cartoon inside the Rydberg electron's orbital radius. Right, so in the top, that image is taken from the experimental paper cited below. You see in gray, that is the Bose-Einstein condensate of maybe 100,000 atoms. And the orbital radius of the n equal 110 state is shown in blue, and for the 202 in red. Right? So we can be in a scenario where there's about 100 or 1,000 ground state atom inside of the Rydberg atom. One might intuitively expect that that should immediately kill the Rydberg atom. Right? The reason that's not happening is because in a Bose-Einstein condensate at nanokelvin temperatures, even that many ground state atoms typically don't really have the energy to even change the electronic state of the Rydberg atom, let alone ionize it. Right? So what experiments have seen is that there is some reduction of the lifetime of the Rydberg atom, maybe in the range of a half or factor of 10. But overall, we're really still looking at a Rydberg atom sitting there in the BEC. Now, what happens if these ground state atoms venture into the orbital radius of the Rydberg electron, right? So the blue line there shows or sketches the shape of the Rydberg electron probability density. Now the Rydberg electron can elastically scatter off the ground state atom. And in the same way, like we are simplifying our life when we look at BEC atom scattering, we know that there's only S-wave scattering, so we can use that Fermi pseudopotential that replaces any sort of more complicated interaction potential with the delta function. The same is now possible here for the electron atom scattering. We just have to essentially use the electron atom scattering length. That turns out to be negative. And then the overall potential for the interaction of my Rydberg atom with the ground state atom is shown there at the bottom, this V of R. That's the interaction amplitude, V naught, that contains that electron atom scattering length, times the probability to actually find the electron at a certain place. That's the Rydberg electron wave function mod squared. In a sort of hydrogenic, say n equal 80 state, you know the wave function really has very many radial nodes, right? So now we have this slightly esoteric potential shown there that is sort of net attractive, but it really has lots of rapid oscillations and lots of little local minima, right? So a very unusual potential. I would say the largest activity regarding this potential has been trying to find so-called ultra long range molecules, right? So now can imagine my green ground state atom there is somewhere stuck in maybe this outermost wiggle of the Rydberg ground state potential. And indeed, people have found bound states there, right? So they are also very interesting, but in this talk, I don't, essentially we assume that you avoid those bound states by not detuning your laser in the wrong direction, right? So we want to instead look essentially at the non-equilibrium dynamics of these ground state atoms in the presence of this fancy potential. Are there any questions so far? Please interrupt in that case, right? So now, yes?
Sebastian, can I ask you a question
Hey.
here? Hi.
Yes, please.
So the thing is that when you're looking at the electron, the Rydberg electron, and you're scattering it off the atoms, what is the wave function that you attribute to the electron? I mean,
so I will essentially fix that, right? It's a good question, right? Like what state am I actually in? For this potential, as you see that this V of R, we put a psi E of R, that is one selected electronic state of the Rydberg atom. Most of the time the S ground state, right? So let's say we go to 80 S, M and L, obviously 0. That of course assumes that my condensate or my background is not causing any electronic state transitions after I've excited it to the S state. And that is, I would say, supported by most experiments.
right. No, okay, fine. I'll ask you later maybe. Yeah.
Right, so in this very first part of the talk, I'll stick to assuming that Rydberg state is an S state. Right, so now we want to model this with the Gauss-Pitevsky equation that I had briefly flashed earlier. I don't want to so to take into account that potential that the condensate atoms feel near the Rydberg atom, I'm adding these things in blue, right? So that is now the interaction potential of my BEC with an Rydberg impurity at position xn. And I can have multiple impurities. For the Rydberg atoms, we just simply assume we can deal with them as classical particles. So there's Newton's equation, and they may repel with long-range van der Waals interactions, right? So the Rydberg-Rydberg interaction is some C6 divided by distance to this power 6, right? That will make the atoms repel. And if we want to now figure out what happens to this combined system, the very first effect will be a simple phase imprint. Right? It so happens that that term in the blue box, that Rydberg electron ground state interaction, is typically relatively much stronger than all the other stuff. Yeah? Kinetic energy, say trapping potential or ground state interactions. That means in the first step, I can just neglect all of that. Right? And that resulting Gauss-Pitevsky equation, or if you want Schrödinger equation, I can very simply solve. Right? The solution of that tells you that the condensate amplitude will just gain that complex phase factor that I'm showing there. Right? So you get an e to the minus I interaction energy t after some time t. Right? That just changes the complex phase of the wave function, hence we call it a phase imprinting. Only at later times will all these other terms in the equation then cause more complicated things to happen. Right? On these short times, if we now look at, imagine you have a condensate there in the XY plane. I have a Rydberg atom at the red dot, and I'm just sort of imagine moving that around from that bottom location to that top location in say 3 microseconds. What the simulation here has shown you is that you're just like painting that phase stripe onto the condensate wave function, right? So the color is the complex phase, right? And here we've painted this 0.6 pi phase along the track where the Rydberg atom has moved. One thing we discovered in here is that while of course you can do all of that with that complicated many oscillations Rydberg ground state potential that's shown on the right hand side in black, because of the movement, you imagine that you can probably understand that we are actually averaging over all these fast oscillations when we are creating this phase. So we get about the same result if we take the classically averaged potential that is shown there as a blue or red line, right? So that's just averaging over these black oscillations. And anyone who's ever done this sort of numerics would know that that simplifies our numerics a lot because of those black oscillations, right? And the following, that's what I'll show you. Now, Shivakant has done this nice movie, right? So you have a 5 atoms embedded in a Thomas Fermi Bose-Einstein condensate. The condensate is assumed two-dimensional, tighter than the Rydberg orbit. And as time goes on, you will see these 5 colored atoms now repelling due to the van der Waals interactions. While they're doing that, you see on the right-hand side that they're painting relatively regular phase stripes onto the condensate. If you look on the left, you see what I said earlier, that the density initially isn't much affected. Right now at 7 microseconds, we field ionized all the Rydberg atoms. You assume they're removed, and we're speeding up the movie. Right? And now you see that now this kinetic energy and other terms in the Gauss-Bidevsky equation kick in, and they convert these phase stripes into waves in the condensate density. Right? So now what we've done is gotten some nice clean waves wherever the Rydberg atoms have moved through the condensate. And this whole setup reminded us very much of a bubble chamber, hence my name of that in the title. And it has actually a lot of similarities. Right? So bubble chambers are devices from the early days of particle physics, where you find tracks of highly energetic fundamental particles because of their interaction with the low energy medium in the background. And that really is the same here, right? So the highly energetic Rydberg atom is moving through the low energy BEC, it's affecting it. And by reading out those tracks, I can infer what's going on. We believe that also, I mean, so these bubble chambers or generally particle physics tracking devices are used to learn about fundamental physics. And I think the same can happen with these Rydberg bubble chambers, right? So for example, if you want to learn a little bit more about Rydberg atom interactions, one thing they do is if they're attractive, they move towards each other and then very quickly ionize. So now we could look at some of these attractive tracks there on the left-hand side and then see the ionization distance. Alternatively, there could be inelastic processes that change the angular momentum state of these atoms. They have been observed in experiment and in something I'll tell in more detail in a later part of the talk, right? So this interaction potential depends on the angular momentum state of the Rydberg atom. So if your angular momentum is changing, then the imprinted phase should be changing. Okay, are there any specific questions about that first part? Maybe before I move on to the next one.
Sebastian, if I can just ask, so
Yep.
in this situation, in the 5 tracks that you showed, I mean, it seemed to be all the interactions was repulsive, but this is not necessarily the case. So this was just a choice you made, or?
That's a choice. Yeah, all the interactions are attractive, repulsive. I think I can make that choice experimentally easily if I excite only S states. They, for the right principal quantum number, are repulsive only.
Oh,
Once you mix in any other electronic states, it gets more messy, right? I would say that also gets more interesting for the experiment, but for theory, we don't like it because once the atoms attract, right, the numerics becomes really annoying.
So,
right? So there we just.
If we were preparing the Rydberg atoms, I mean, you would typically prepare it in a single state, and then you could, I mean, and if you take care to prepare it in the S state, you would see a pure repulsive behavior. This is what you're saying.
Yes,
okay.
That's what I'm saying.
Thanks.
Right, but I'm also like you said, right? It would possibly be more interesting in experiments to also throw in the occasional P state, and then get more complicated dynamics. Right?
Yeah,
That we can't even do the theory conceptually, right? So that gets actually very interesting. I'll show you some of that.
Okay, super.
Okay. Now, experiments, I would say, are still challenged by what we are proposing there, partially because you need relatively high resolution, and also because I think some slightly important aspect of our simulations is that they're in 2 dimensions. Right, so we were, of course, very excited when we learned that the group of Tilman Fau and Florian Meinert in Stuttgart are actually trying to do this, excite the Rydberg atom, and then see in detail what it does to the BEC in a 3-dimensional setup. So we have sort of attempted to model their experiments. Let me tell you in very brief only how they work, right? So you excite a Rydberg atom at a specific place in a huge cigar-shaped BEC. You then let it sit there for a short time, or they let it sit there for a short time, say 3 microseconds, after which it's being field ionized. In that time, it has created that little disturbance that I'm showing there as a sort of bright white spot in the BEC cloud. And then one lets it sit there for another 200 microseconds for whatever dynamics has been initiated to develop, like these ripples in the movie that I've shown you earlier. And then they do in situ phase contrast imaging to essentially take the column density of that BEC. Right, so we can see in exactly the spot where the Rydberg excitation has happened, what happens to the BEC density. Right, that is an experimental image kindly provided by them, where you see in blue that essentially entails a density reduction compared to the case where you had not excited the Rydberg atom. Right? Yellow is sort of neutral, nothing much has happened. Density has stayed the same. Right? There is a sort of very faintly visible dotted circle on the image that is the size of the electron orbit in the chosen 133 state.
Hi, Sebastian. There is a question in the chat box. So Manju,
Yes.
Can you unmute yourself and ask the question directly?
Yeah, sure. Hi,
Hi.
Sebastian. Can the Rydberg atom destroy the condensate? You said highly energetic.
That's a good question. I mean, certainly one would first suspect that possibly yes. I don't think it's super obvious to say why not. So our simulations say that not. Right? You get some heating, but you don't get really dramatic heating. So we have simulation evidence, and I think there's also experimental evidence that right, so condensate destruction type of stuff is under control. But that's for a few excited Rydberg atoms. If you keep doing that, I think you're right. You probably. Okay, so currently my belief is that a few Rydberg excitations would not necessarily destroy anything. Of course, you get local heating, you're creating uncondensed or thermal atoms at the point of insertion.
Okay. Thank you.
Right, so now essentially in the experiment, they want to find out in more detail what happens there at the insertion point. And you see that image there is still relatively noisy. So what they have resorted to also in earlier experiments is instead of exciting it only once, right, you can repeat this process multiple times. Right, you put the Rydberg atom in, you let it stay for 3 microseconds, you whack it out, you start the next one. Right, so we do this 20 times and then take the image after a 200 microsecond wait, and then you see this relatively nicely defined density depression developing at the place where you expect it to develop. Right, now the question is, do we actually expect the density depression to develop? So that we try to answer by doing these 3-dimensional Gauss-Pidevsky simulations. Right, so that's the same equation I've shown you before on the top. Right, you have your usual Gauss-Pidevsky equation plus the interaction with now a single Rydberg impurity only at a location xn. And that location xn we choose randomly for these 20 excitations within what we expect to be the laser focus region. And right, so there's more controls than just the laser focus, but they will not all be exactly in the same place, only roughly in the same place. At the bottom, I'm showing you the slice through the BEC density in the top and the column density at the bottom. So column density means I'm averaging from the top to the bottom along the line of sight through the BEC. Right, and all of these sort of agree on that wherever the Rydberg atom has been thrown in, you create these ripples. And then if you wait a little bit longer time, these ripples cause huge waves going out. Right, but you also see that one essential feature doesn't quite agree with the experiment. So if you see that black circle, that's like a density depression. That's what the experiment sees. Right, but we consistently have one issue of disagreement with that. That's this density increase at the very center, which is relatively intuitive. If you look at the right-hand side cartoon of the potential, right, it's a net attractive potential. Yeah, so as you are putting these Rydberg atoms in, you're essentially pulling your BEC atoms towards the center. And then if you wait for the right moment, they'll all clock up there at the same time and cause a density spike. Right, so that seems to make sense. So we're still essentially trying to figure out why the experiment does not see that. Right, so this might be a handle on some, or a window on some so far not quite understood atomic physics regarding the interaction potentials, or possibly like you were suggesting, right? If you asked how does the BEC get destroyed, maybe there's some non-mean field physics happening. Right, we have looked at that as well and haven't found any, right? But I'm not sure I'm confident to rule it out 100%. But certainly what we can tell is that this is a very interesting setting to explore further. Are there any questions about that bit before I get to the last one in the last 5 minutes? Or actually more like 10 minutes. Okay. Right. So all of this so far, we had talked about inserting a Rydberg S atom in a BEC. Now I move to possibly inserting two different angular momentum states, S and P. Right. So essentially, I'm turning my Rydberg atom into a qubit for those that like quantum information, or a spin system. Right. So I can call the S state spin down and the P state spin up, and I will do that in the following. So please remember. And then the important difference for the present purpose between the S and P states, I mean, there is an energy difference that's actually not so important. But importantly, the electron orbit changes shape, right? You all know that the hydrogen S state is isotropic, right? It's just the same in all directions, whereas the angular momentum 1 m = 0 state has the shape of that dumbbell, right? So the overall probability density has a cosine squared dependence. Right, and that looks like that orange block. However, all the rest of how these Rydberg atom interacts with the BEC remains the same as what I told you before. Right, so whenever the ground state atom is in the orbit, it can be kicked by the Rydberg electron. But we now expect that in these two states, we are imprinting a different pattern. Right, so on the left, you should have a sort of isotropic pattern imprinted by the S state. And on the right, if you maybe don't focus on the small oscillations, focus on the bright white color, right? In the right, that is imprinted by a P state. You can sort of guess that cosine squared dependence of the electron probability density. So the imprinted pattern will be different. Now, it's a kind of cute question to ask, what if we put that Rydberg atom in a superposition state? Sorry, that's a totally nonsensical state, I realize now, right? So there on the bottom left, that should read spin down plus spin up, of course. Right, so we put the Rydberg atom into a superposition of S and P. And I can easily do that in experiment, I believe, right? I excite it in the S state, and then you drive a short microwave pulse until you are in the S plus P state. Right? Now we still want to do this phase imprinting, but we have only one mean field available. Right? If we say all the Bose-Einstein condensate atoms are in the same state, I have only one mean field. So it's highly likely that for this scenario, we'd have to go beyond mean field theory, and we will do that now. Right, so we actually start from scratch, from nasty many-body physics. Right, so you write your many-body Hamiltonian with an atomic field operator, there psi k of x, that destroys an atom at position x in electronic state k. And this k can now be the ground state in the cartoon on the left in green, or the S state or the P state. Right, and in all these states, there's different interactions involved that we can take into account. Yeah, but most importantly, we now put the ground state atoms into the BEC plus fluctuations using the usual Bogolubov approximation. Right, so I write my ground state field operator as the mean field plus sum over Q. These are the wave numbers or momenta of my phonons. Right, and these quasi-particles around the BEC are called phonons or Bogolubov quasi-particles. And these B operators create now quantum sound waves or elementary excitations of the BEC. We plug that into the Hamiltonian and then find the simplest form relevant to the scenario where I have a Rydberg atom in either S or P state or superpositions of those. Right, and what we find is known as the spin boson Hamiltonian. Right, so you have the part describing only the Rydberg pseudospin, that's sigma z. So the first term, that delta E, is the energy difference between the S and the P state. Each of these phonons gets an energy just like a quantum harmonic oscillator there in this H environmental. And most importantly, at the bottom, you get that interaction term. Right, so now depending on whether the embedded Rydberg atom is in S or P, we will have a slightly different excitation of these phonons. That is what that Hamiltonian tells you. Right, and if anyone is interested, so I put lots of things under the carpet. That's what that carpet icon is supposed to symbolize, that are not relevant now for the explanation, but may be interesting. Do ask or look at the preprints. The fact that multiple electronic states in a cold impurity in a BEC give rise to this spin boson model has been pointed out before by the groups of Jaksch and Levenstein for ground state atoms. So the new contribution here really is that we can calculate these coupling constants that are the essential part of the model for the case of Rydberg interactions. If you look at the form of these, this is slightly important, they contain something like a Fourier transform of the difference of the Rydberg electron probability density in P and S. That's of course ugly to calculate. So after all the hard work, we wanted some sort of method to verify that our calculation was right. And we found one that we really like a lot because it also gives rise to some sort of new insight. For that, if you look at this spin boson Hamiltonian, you realize it's actually diagonal in the spin. Right? So there is nothing here that couples the Rydberg S and the P state. The only operator is sigma Z that is diagonal in the spin. That means I can write my whole nasty quantum many-body Hamiltonian, whatever it is, I can write it as two blocks like shown there, one for spin up and one for spin down. I therefore can also write my many-body wave function as something to do with spin up and something to do with spin down. Right? So in this equation, this is a many-body state where the left-hand side of the tensor product is my Rydberg state. Is it in P or S? And the right-hand side is whatever quantum many-body state my Bose-Gas is in. Right? So the right-hand side state from the tensor product is the BEC. We could, for example, now look at the coherence between the P and the S state. That's something that experiments could read out relatively easily. And if you do the fundamentals, you find very easily that this coherence is given by the overlap of this Bose-Gas state for the case of having the P atom in it or the S atom, like is shown there. But now we are in the comfortable situation that that overlap we can calculate in two different ways, at least. One is we just analytically solve the evolution of that Hamiltonian. That is nasty, but possible. And the second approach is we go back to the earlier part of the talk where I had convinced you or told you implicitly that if I have just the Rydberg atom in a single electronic state, I can just use mean field theory, your Gauss-Pitaevsky equation. Mean field theory is based on the fact that I say all my n atoms are in the same single particle state. And that's my mean field state, mean field wave function. So I can actually reconstruct something like a many-body state shown there in the bottom right. That's the psi from the mean field wave function phi. And after I've done that, I can again calculate that many-body state overlap that gives me the coherence there in the center equation. So I do that either with the Gauss-Pitaevsky equation, two Gauss-Pitaevsky solutions for S atom or P atom separately, or this spin boson model solution. And what we find is they very nicely agree. So we are happy that we probably did the calculations right. This then puts us already in the position that we can, for example, predict these Rydberg superposition coherence times in the BEC. And in something that would not surprise any Rydberg person, these are highly tunable. So at low principal quantum numbers, they're a lot shorter. So something like 20 nanoseconds at n equal 40, and they approach a microsecond at n equal 120. So we are confident that there are at least some range of principal quantum number where they should be a lot shorter than other stuff that we haven't looked at. Of course, there's always more than one decoherent source. One thing that is now very interesting is if I wind back to this many-body state, this already tells me this is the root cause of decoherence. So if you look at any decoherence in quantum science or technology, it's because your qubit here, spin up, spin down, has become entangled with the many-body environment. I'm not measuring the environment, so I get decoherence. So we had the crazy idea, can it be possible in this nice and clean and relatively coherent environment setting to see this effect? So now if you imagine I have that superposition of the stuff to do with P and S, so the spin up, spin down in the right-hand side equation. And I bring the spin state back into, say, only spin down and then de-excite the Rydberg atom. Then my BEC wave function should be the one shown there in the top left. That is a quantum superposition of psi up means I had a P atom in it and imprinted the P phase pattern. And psi down means I had an S atom in it and imprinted the S phase pattern. And we try to see if some simple experimental observable, such as a column density, should show a difference in this massively entangled or mesoscopically entangled many-body state compared to some boring average of you 50-50 average the P and the S imprint. And we find a difference that is shown there in the left. That's how it looks like. And it's very faint. So it's something like 3% of the actual quantum density, but it's there. And it lives as that sort of the curve on the right-hand side shows you the amplitude of that signal. It's a transient signal that happens while you're decohering your system, right? So we think this is a very nice glimpse at, if you so want, the decohering interface between a quantum system and its nasty environment. That I'm not aware of any other platform where one could hope to see it in this way. Due to time constraints, then I didn't have, right? So there are other exciting things that you can do with that Rydberg atom in the BEC, or that we have worked out there, right? So if you want to treat that Rydberg atom as a generic open quantum system, you typically need all sorts of correlation functions and spectral densities, which we calculated for this system. And then you can make it a little more complicated and microwave drive the Rydberg atom between S and P state, like in that bottom box. Then you need some advanced solution methods for open quantum systems, like non-Markovian quantum state diffusion, which we have used to show that there's interesting non-Markovian response of this overall system. Right. With that, I'm through. I'd like to thank all the people that did the hard work, our experimental collaborators, and also everybody else in the group just for their enthusiasm and all sorts of other projects. I'd leave this summary slide here to remind you of the key points again, and then I'd like to thank you for your attention. And I'm happy for any further questions.
Yeah, I think we have time for a few questions, 2 or 3. So if there are any questions, you can unmute yourself and then close the question. Yeah, looks like there are no other questions. Hi, Sadiq, you had a question. Do you want to ask it now?
I have asked my questions, actually.
I see. Okay.
Yeah.
I thought you wanted to follow it up later. Okay, good. Then, Sebastian, I have a query. So in the later part of your talk, you were mentioning about these Rydberg atoms in S and P. And then in that context, you had introduced the spin boson description.
Yes.
But if we think about S and P Rydberg states, then these are in terms of the orbital states. So
yes, it's a pseudo spin. I'm not talking about the real degree of freedom. Right? So I just here in this cartoon, I just label the S is spin down, the P is spin up.
Okay.
You're right. So we're not not looking at any of the gory details of angular momentum coupling.
Yeah, then fine. I have another. Now, supposing if we take the case of this P state Rydberg atoms, now supposing if we take the case of the group 1, that is the alkali atoms, then their ground state is the S. Now, if we excite Rydberg atoms to P state, then will there be some difference in terms of the lifetime compared to the Rydberg states in the S state?
There is a difference. It's not dramatic as far as, so in vacuum, I think the P states are typically lived longer by a factor of 3 or 4 or such. I guess, yeah, I couldn't run you through the details exactly why that is.
Okay, so the physics will not be affected too much.
I don't think so. So we are trying to take care that whatever we say. So for example, when I'm showing you a decoherence time, that is of course shorter than the radiative lifetime of that Rydberg atom. And in particular, then you have to be careful once you put them into the Bose-Einstein condensate. Lifetimes are even shorter, of course, than in vacuum, right? But they are still surprisingly long, right? So it can be still several microseconds. So certainly the coherence time in the nanosecond range will be featurely less than the lifetime.
Thank you, Sebastian. So it looks like there are no other questions. Then, yeah, great. Thank you, Sebastian.
Thank you very much for being here. Bye-bye.
Okay. So now our next speaker is Manas. Hi, Manas.
Hey.
Hi.
You can hear me?
Good afternoon. Oh, yes, I can hear you. So, okay, let me give a brief introduction of Manas. So Manas did his PhD from Heidelberg University and GSI Darmstadt, Germany. Then after that, he did postdocs at various places. And then later on, he took up a position at IACS, Kolkata. Then he moved to National University of Singapore. He's there since 2012. He has a lot of interest in precision spectroscopy and the application of those for fundamental physics. So today he will be talking to us about exploring a single qubit space for sensing and quantum machine learning. So let's hear in more detail from Manas. Yes, over to you, Manas.
Thanks, Dilip. Thanks for the nice introduction. And I would like to thank, first of all, the organizers for putting up this brave effort in these difficult times. And I know how much, I only know partly, how much they're like fighting every day on both inside and outside running the school. So I would, so what I'm going to tell today is maybe try to motivate that while we scale up quantum computing or quantum information processors, I think it's also important to see how good can we use what we have. And in this particular case, I am more interested in exploring the space of a single qubit. And as I will show you that it is indeed possible to use the single qubit to perform things which are not possible classically, or in some cases, even in certain quantum scenarios. So here are two examples kind of taken from our recent work. One is the sensing. The other, which is we are also still learning, is machine learning. And the good thing is that being in CQT, we have people coming from computer science. So we get kind of infected by the language of computer science. So please bear with me as we go along to learn more about the possibilities that we have using single qubit for machine learning. Okay, so before I forget, I must say that the wonderful data that I will show you later is an outcome of a dedication of many people. Of course, those who are marked in red are the data that I will be showing today. There are other projects where others are involved and helping in running it. Of course, as you can imagine, nothing in the experiment would run if there is no fund. So we are funded by NRF as well as MOE for different projects. By the way, Dilip, if there are questions, do let me know. Yeah, I can stop any moment.
Okay, and one more thing. Would you prefer audio or chat box?
Anything is fine.
Okay.
Fine. Yeah, just if necessary, just stop.
Okay.
Okay. So what is it? It's a two-level system. As we know, it's a qubit. And in our case, we work with barium plus, Ba plus. This is roughly the energy level diagram you would often see. And throughout the school, those who had attended it have also seen it many times. And this is more or less the same in calcium. You would find more or less similar in beryllium, a little bit different, but more or less you will see the same structure. And for us, the qubit is between S half and D5 half. So that's why we call it an optical qubit, because it is we need a laser. In this particular case, it's roughly about 2 micron, 1.7 micron to drive this transition. And the other thing is that this is a D state is a very long-lived state. In our case, it's about 30 seconds, which is good and bad. Good in the sense that your coherence time of your qubit is very, very long. Yeah. The bad thing is that you need a very good laser to drive it. Fortunately, we have it. So what you see on the left side is a spectrum from this transition S to D. And you see we get a line width of about 120 hertz. And this is mostly because it is magnetic field sensitive transition. So the magnetic field noise leads to this 120 hertz around clock transition. So once you have that, then you look at the other performance indicators. For example, the dephasing time. This is the Ramsey spectrum. The black curve you see is the Ramsey spectrum when our whole cycle of the experiment is locked to the line, which is 50 hertz. And the red one when it is not locked, which means that the 50 hertz noise somehow is seen even though it is very small, is seen by the ion, and that leads to the magnetic field dephasing and leads to the decoherence or dephasing. But if we could lock it, of course, that means that the whole experimental cycle would be longer, but we can get to long coherence time or dephasing time. Our heating rates are relatively low. These heating rates, again, I would like to remind you about what Christian Roos had told you or Liefried has told you before. This is the heating rate that the ion sees because of God knows what, because we don't really know yet, but because of the surface effects or some technical noises. It is very low in our case, not because we have done anything great, but it's just because the trap is fairly big compared to where the surface effects come into play. The right side is the gate operations. These are single qubit gates, and what is being shown is randomized benchmarking to roughly tell you the number of errors that you gain as you run more and more gates. Of course, this is a very old data. As I will show you in the next section, it's two parts. So when I talk more about the computing part, you will see that this has improved in the meantime. Then, of course, there is a focus on the scaling up as well. So what you see down there is a 30 qubit system, which is not, we do not run any qubit operations as of now on these 30 qubits. These are more for stability operations of the trap. However, we plan to do it in next few years. Yeah. All right, so in ion traps, you have also seen that apart from the internal states, the S and the D, which is the qubit, you have the external motion as well, which you have learned quite a bit throughout the school. I would not get into the details. In our trap, the dimensions roughly are about the R0. If you may like, the distance between the blades is roughly about 500 microns, so 0.5 millimeter, and the end cap to end cap distance is about 1.5 millimeters. The trap is ran at a frequency of 20 to 25 megahertz with a voltage of around 1.5 kilovolts. Yeah. This gives a secular frequency of about 1 to 2 megahertz. So those are like the vital parameters for the trap running. Essentially, for what I'm going to say you in the next 15, 20 minutes has more or less nothing to do with the motional state. We do use motional state, but for what I'm going to tell you now, we don't need to know about the motional states. We'll mainly concentrate on the two-level system and on the qubit space. Yeah. Okay, so what I'm going to say now is divided into two parts, as I said. First of all, I will talk about the sensing application. What is shown here are just two levels. Now, if you have such a two-level system, you can use it as a clock, as I've shown you before. However, imagine that you have a background which is giving noise to the ion, and it is a time-dependent frequency. So if you have a time-dependent noise, the goal here is to measure the amplitude as well as the frequency itself. Now, is there a measurement that we could follow, or a protocol that we could follow, which allows us to go beyond the classical limit of precision for the frequency measurement or the amplitude measurement? In other words, let's put it in the context. So suppose you have a B field and you have a spin. So we could write down the interaction as B dot S. Now imagine that the B is composed of a B naught and a B modulation, which is modulated at a frequency of small omega. What we intend to find is the B naught and the omega. Sorry, this is a mistake here. We intend to find the B mod and the omega. So the modulation amplitude and the frequency. And we want to know how small can the uncertainty be of these two measurements. Well, as we go along, I would only concentrate on the uncertainty on omega, but similarly, one could find the uncertainty on B modular. Okay, so the Hamiltonian, what we actually use is not exactly the B, but one could use the B. What we use is a sigma Z and omega D sine omega T sigma Z. So it's the same effect. The only reason we don't use the B is because for us, it's easier to have AC stock shift modulated rather than the B field modulated. Well, the question that we are actually asking is, there is a story related to it. And again, it's a private communication. I don't know how much it is true, but what I said was before the G-2 experiment on electron, when Demelt actually put up his proposal to the committee asked, as usual, you are asked for a scientific proposal to tell how long it takes to build the system. But he was asked like how long it would take to get the uncertainty down to 1 Hertz. And his answer was 1 second, based on the scientific merit of it, even though that was not the intention of the committee. Now, the reason why it is 1 second is because if you think from the physical point of view, if you have upper state which has a energy uncertainty of corresponding frequency of 1 Hertz, you would need 1 second to measure it to the level of 1 Hertz. Yeah. That's the energy uncertainty principle that would tell you that. Now it comes from another direction as well, which is the quantum or information theory. So the variance of a parameter alpha, the alpha could be the B modulation or the omega in this case. The variance of that is, the minimum value of the variance is proportional to 1 over n, which is the number of measurement, and 1 over f alpha, where f alpha is the Fisher information, which is bounded by the Kramers-Rao bound. And this is, as you can see, this is a very, very important paper in information theory. And it goes back to 1945, published in Bulletin of Calcutta Mathematical Society. So the F alpha is actually the content of information that is present in a parameter alpha. And the quantum information, Fisher information, is given by this formula here, which actually tells you that how fast the state changes by a small change in alpha. So that's what the Fisher information tracks. And if you have a time-independent Hamiltonian, it is easy to show that F alpha is proportional to T square. And when you plug it in, you get the standard deviation to be square root of this, and therefore you get 1 over T. Okay, so the quantum Fisher information is this. Now, if you use a single probe, and the best thing to do is to use a superposition state, which is given by the probability amplitudes of probabilities of P0 and P1. So the Fisher information in that case turns out to be 4P0 P1 multiplied by the rate of change of the phase with the change of alpha, or the parameter. Yeah. Square of that. So, which means you can maximize your Fisher information by creating an equal superposition state. And that's what we all know, because that's how the Ramsey technique works. And that's where it comes from. Now, if you think of the standard deviation or the uncertainty, it turns out to be the minimum uncertainty is 1 over T, assuming that you have only one probe or you have made only one measurement. Okay, there are various ways to beat it. And one of the simplest way is to increase the correlated. So these are uncorrelated measurements, N. Now, if you make correlation in the measurements or in the probes, you get 1 over N instead of square root of N. This is one way where entanglement helps. The other way is more trivial way. If your Hamiltonian has an explicit nonlinear time dependence or exponential time dependence, for example, e power t sigma z, you can show that the variance can scale as 1 over t power gamma. So what we are interested in is none of these. We would like to use one single probe, one measurement, and we would like to see for a time-dependent measurement whether we can scale faster than 1 over t square, or 1 over t. Well, in order to do that, the first thing to do is to ensure that we are limited by the statistical uncertainty, not the systematic. Because if we are limited by the systematic uncertainty, there is no hope to see the scaling. In order to ensure that, what is plotted here is the number of measurements as so the phase, the uncertainty in the phase measurement for our qubit as a function of the number of measurements, independent measurements taken. And you see that this scales as 1 over square root of n, which means up to certain time, we do see limited systematics below the statistical uncertainty. So this is the regime where we will work at. Now, what is the standard technique? I'm just repeating, Christian Roos has already told you before, but just to make things complete, what you start with is an initial state of 0. You create an equal superposition of 0 and 1. And once you are in the equator of the Bloch sphere, there is free evolution of the atomic qubit. And at the same time, the laser is also evolving in the same plane. Now, if there is any noise which leads to a lag or a faster change of the atomic qubit or the atomic state, which is given by the red arrow here, this phase between these two is what we measure in an experiment, and that's this phi alpha. Of course, the sensitivity of that measurement also depends on which final state you project it to, and the choice of the final projection is also important. So that's the general technique, Ramsey technique, which is followed for any clock measurements or any phase measurements. All right, now if we apply and do the same for this Hamiltonian to figure out the frequency small omega, we would end up in a quantum Fisher information that scales, as you can see, with the number which is somewhat 1 over t, provided you have measured it at certain particular time, or in this case, time is written in a slightly different manner. But in each of these oscillations, you would only get to 1 over t, provided you could measure it at certain particular times. Okay, so what are the ingredients? The ingredients are that we need to start with the equal superposition, and then we have to project it such that we get maximal information out. Now, in this particular case, as you can see, the Fisher information, if we calculate it out, is the difference of these eigen values of this Hamiltonian, which is oscillating with time. Now, if you look at this difference of mu max at any point t, at any time t prime, minus mu mean any point t time, this is roughly 0. And that's the reason why you would not see much of an increase in the Fisher information, and hence your uncertainty will be scaling only 1 over t, but only few cases where there is a small change between the first cycle to the second cycle. So there was a proposal forwarded by Pang et al., Pang and Jordan in 2017. And the nuts of it is that one way to enhance it is by changing the sign of this minus to plus in every cycle. How do you do it? You apply controlled pulse at the antinode of each of these eigenvalues, which means those who are familiar with spin echo, in a spin echo, your purpose is to remove the noise, and therefore before it crosses, you flip by pi pulse to the other side. In this case, it's just the opposite, because you want to increase the phase gathering every cycle, which means your pulse sequence is now have to be shifted by pi by 2, and which is this sequence just tells us. So this is again the same thing. We run first the equal superposition state, then the qubit evolves, and as the qubit evolves, we perform this feedback mechanism of applying a pi pulse every pi by 2 of the cycle. And if we do that, then we could actually gain more information in the same time. Now, how does that scale? So in order to do that, this is just the determination of the gradient of the change of phi as a function of alpha, in this case, the omega. So we change the omega, which is in this case given by f. As a function of f, we see that the phi changes, and these are measurements done repeatedly to get the uncertainty lower. The slope of this gives us the quantum Fisher information. If we now plot the slope where the red dots are uncontrolled, where we have not applied the pi pulses, we see a scaling which is 1 over t. And this is not surprising, that's what we expect. But when we apply the pi pulses, we see that the Fisher information, which is just the inverse of the uncertainty, scales as 1 over t square up to a time of about 80 microseconds. And after that, the systematic starts to play. In this case, the decoherence of the system when we run very fast single qubit rotations. And this has to do mainly dominated by the instability in the laser power. Each of these the get time is about 1 to 2 microseconds. All right, so that's the original paper, and then very closely related but not the same is where you have nonlinearity in the Hamiltonian itself. Then you can actually use that nonlinearity in order to develop what is called lock-in amplifier, which is partly classical and partly quantum. While there has been one experiment on superconducting qubit to get a scaling very close to 1 over t square. However, if you use a superconducting qubit, the difference is that the ion is sensitive to an external field. And that's where our interest comes in. Because if you look into literature for the dark matter search, you will end up in something called axion-like particles, dark matter, and these are light mass. In fact, it is claimed that these particles are flowing through us, we just don't realize them, and it should be flowing also through the experimental apparatus, including the ion. Now, when it flows through the ion do see a classical field, which is more or less given by this term here, where you see there is a time-dependent part and the sigma E, which is the either the spin of the electron or any of the angular momentum of the electron that couples to it. So if we apply that technique and look at the limit that we can get even with a single qubit, we end up somewhere here. Now, the interesting, so what is this plot tells us is that this tells us what is the coupling strength that we would expect if we would have seen a signature at a given frequency. Frequency here corresponds to the mass of the axion-like particles. So that's given by the color code here. So the lower coupling, which is around the blue, is where things becomes very interesting in terms of the new physics. We stand here. However, I must say that there is till date no direct measurement of the electron coupling to ALP particles, because this GE, this coupling constant GAE is different from those of the nucleonic coupling. Now, one could actually use the same technique and the protocol to enhance by increasing the number of atoms, which certainly is not a possibility for ion traps, but could be a possibility for a gas cell, for example. On the other hand, the coherence time may be compromised in that case. Okay, so is there any question up to here? Okay, so I don't know if I don't hear or you also don't hear.
We can hear you. Looks like there are no questions.
Okay, perfect, perfect. Sometimes, you know, I would be keep speaking, but
yeah.
Okay, good, good, good. So I would then switch topic from here. And this is a little bit of big switch, I would say. So now I'm going to tell you that single qubit is also very, very good to be explored in terms of machine learning. Now, here is a kind of a pictorial depiction of a quantum computer, if you may like, or a quantum circuit, if you may like. Each of these are qubits, and they this is time. You start by doing single qubit operations on them, and then 2 qubit operations, and then again single qubit operations, and so on. So that's the depth of the circuit, and this is the width of the circuit. Now, there is also the color code here. As you go in depth, you see that it becomes hazier because there are errors that comes in, and that's where we are presently at. It's called the NISQ era. So these are noisy devices. Now the question is it good to go this way, or is it good to go this way? Ideally, it is good to go diagonally, meaning having both. Yeah. So our present, just our own present interest is actually probing more on the depth and finding out problems which might be interesting. Because if we understand that, we could eventually go on the scaling, even with a smaller number, to see certain problems which could be interesting and can have certain advantages. So what I'm going to tell you about is classification problem. Now, classification is a problem which is everywhere. We can't avoid it. And it starts when we are very young, right? So this is a task given to my kid some days back, which asked him to circle the living things here. Now, well, a human being, he would, after a few trials, would eventually...
I'm not able to hear you.
Are you not able to hear me? Oops. Is it better? Hello?
You are audible to me.
Oh, I am audible. So then it's Dilip's problem. Okay. Okay, good. So you see, a child or a human being would be able to eventually classify it by looking at it and learning from it, and then able to apply his learning to understand what is living and what is non-living. Now, if you have to come up with an algorithm to do it, this would, or this actually is existing. It looks like this. You find the features that are associated with each of these objects, create a feature vector space, and then use this, this vector space to apply certain planes to see that we can distinguish between different features in the vector space. And this is presently done by several means. So the first one is a very widely used classical compute, which is called a state vector classifier. You could have neural networks like convoluted neural networks, or nowadays what is most relevant is a deep neural network. So well, the purpose is that there are two parts. You use these to look into the feature space and then distinguish in the feature space the different types and classify them. And that's it contains two parts. One is the learning or the training part, where you give data and the machine learns, and then it uses for verification. Now, if we look into a little bit deeper into the neural networks, we would be able to understand where the problem comes there. So this is an architecture of a neural networks. Each of these are the neurons where certain compute happens, and it gets input from the previous nodes. These are called the hidden layers. You can have one or many of these layers. Now, what is actually done in this hidden layer is the following. You take the vectors from the previous one, V prime, put some weight A and B, and calculate a nonlinear function of what you have been given at each node. So now, if you do that, then keep on doing it, you should be able to eventually get a target function which mimics a particular class. And that's how you distinguish between different class, by changing the weights. And this is the training part of it. Now, it is information theoretically, it is possible to show that even a single hidden layer is, in principle, a universal classifier. However, the problem is, in order for complex classification, this requires you to a very large number of these nodes, very large meaning infinitely large, in order to classify complex problems. So we also know that some of these complex classification problems are NP hard. Now, last year, Jose Latorre and his group came up with an alternative where, so I must say that there are alternatives also on a state vector machine which could use quantum. However, we are looking into only classifier based on what is called a data re-uploading. Now, in this case, the concept is very simple. You start by encoding the data that you have, the classical data from the feature space, into the qubit space by the rotation angles. And that's given here. Xi is the data. You apply some weight to it, and then add some weight, and you have a unitary operator. And then you apply these rotations sequentially, but you have to ensure that each of these rotations are non-commuting. If you do that and then train your machine by changing these phi i's and theta i's, such that a given set of data which belongs to a particular class ends up in a particular point or close to a particular point in the Hilbert space that you are looking at. More or less, looking at this is the following, that you have your data tells you how you rotate in the Hilbert space, but then all the red dots would end up in here, while the blue ones would end up in here. That corresponds to class B, and this corresponds to class A. Well, let's look into, this is a very preliminary data. We started working a couple of months back, and then we see, what you see here is a very simple problem where we intend to separate classes which belongs to the center of the circle or inside the circle and outside the circle. And the left side shows the simulation, because you can, we are not telling anything which is not possible by classical computers. Of course, it's a single qubit, you can simulate it. And if you do that, you get this. On the right side, you do it on the actual quantum processor, and you end up in this classification. Of course, a circle is relatively simple if you think of the symmetry of a qubit. However, we looked into more complex classes. This is a 4 class. And what is more important is it a non-convex boundary. This is a non-trivial problem, and it is considered to be NP hard. However, we see that this single qubit can distinguish it very well. Yeah. We also have done what is called supervised learning, meaning we optimize the space of the optimal values of the training data set, and we ended up, you see the red dots are where we initially started it, and the minimum value of our error function ends up in here, while in this space it ends up in here. Of course, what is more important is that when we have big data sets with many parameters, it is the feature space becomes higher dimensional. And this is one example where we start to see the limitations. And this is with one single layer, and then you—
Hi, Manish, you have 10 minutes.
Okay, I am nearly close to that. Okay. So when you have a hypersphere, this is a 4-dimensional feature. And what we intend to see is that are we able to classify those which are inside the hypersphere and those which are outside. Now, it is not very easy to actually to show it in figures or in graphs. So what we did here is a histogram of the points which are within a certain radii. Now, if you see that with one single layer, the overlap region tells you the error in our classification. If we increase to 2 layers, it is better. In 3 layers, it's even better. And in 4 layers, we are nearly there. And at present, we are trying to see that how far we can go. Okay, so that brings me to the conclusion. So what I tried to convince you with is that with a single qubit, you can go beyond the standard quantum limit, which is given by the red line here. And you can do particularly noise frequency measurement that goes beyond the standard quantum limit and scales as 1/t². With the same single qubit, you could actually do classification of data. And as a kind of side note, we most often talk about scaling in terms of either speed or in terms of the number of qubits. However, we tend to underestimate that at present our classical computational limits are because of the energy consumption. And in this particular case, what we are really looking into is the possibility of using the nonlinearity of the qubit to substitute, for example, a deep neural network for which the node calculates the nonlinear function, which requires substantial large number of resources, could be done without much effort with a single qubit. So that is more or less the take-home message that I would like to convey. I am done with this. Thank you for your attention, and I would love to take questions if there are any.
Yeah, so we have time for a few questions. So if anyone wishes to ask a question, maybe you can unmute yourself and then ask.
Yeah, hi, this is Saikat. I have a question.
Yeah.
Yeah, Manoj, so regarding the earlier part of the talk for the detection of axions.
Yeah.
So that part I was a little confused. So how your phase precision relates to axion? Do you have a so is it?
Yeah. So you see here, right? This is the Hamiltonian, which is substituting the Hamiltonian of what I showed before, which is the here. So when you have the background action field, right? This is the action is taking place of this, and the omega is the mass of the action.
So that's the question I have. Is it taking place of this? It's added to this, right? So the question is really the relative ratios of the two Hamiltonian. You still have this evolution.
Right. Of course, we did not see anything, right?
Yeah, but the question is really how can you separate out this free evolution or the usual unitary to actually extract that small little.
Right. So what you do is you change the frequency, right? So if you are in resonance, you would see it going up because the mass is a very, very unique mass. But this frequency which you apply from outside is what you scan.
Okay. Yeah. So your Fisher information still is parameter dependent.
Yeah.
Like that's so basically where your Fisher information is optimizing or maximizing is also where you would like to have your this dark matter interaction to be optimized. Right?
Yes. That's right.
So does that require any special tricks, or is it just?
No. So the problem is if you really have to scan over a large mass range, then this is not the right technique. So usually what you do is if you see a signature without applying the pi pulses, then you can improve on the uncertainty.
Okay.
So you need to have some idea what you are looking for. Now, having said that, if you look into the other work done by Ozeri, which is lock-in amplifier, you could actually combine this with the lock-in amplifier to get to that value.
Okay. Yeah. And from that this part's conclusion, the plot you presented with N and T. And ideally, this in the Fisher information also N and T are equivalent, right? Like either if you can have a good coherence time, if you may wait long enough on a single spin, a single ion, that's equivalent to short measurements on many ions.
Yes. That's right. So the right. So the N and T play the same role, right? More or less, yeah. So let me go back here. Yeah, so you see here the N and T, they play this similar role here. So you can enhance by this and you can enhance by this as well. So the ideal situation would be if you have correlated measurements and also long coherence time. So you enhance here to make it T square maybe, and here also N, which is not square root of N.
Okay. That's fine.
Yes, so any other questions? Yeah, looks like, Manas, we don't have other questions. Here I have just a query regarding the machine learning. So essentially you're using this single qubit to identify quantum system, right?
Right.
Are there some limitations or are there some constraints as to what kind of quantum systems it can?
No. Dilip, maybe there is.
I missed something. Yeah.
Right. So we are not doing classification of quantum states. Okay. We are doing classification of classical data.
All right. Okay.
But using quantum bit.
Okay.
So the machine is quantum, but the data is classical.
Okay.
And it is also not trivial. I did not mention it, but it is not also trivial how we know, like, we're trying to understand now, like, how do you load classical data into a quantum machine? It's not a trivial thing at all.
Right. So looks like there are no other questions. Okay, so Manas, we don't have any further questions.
Perfect.
So thank you so much for
Thanks.
a very good talk. Yeah.
Nice to see you.
Yeah, good to see you after a long time.
Yeah.
Yeah. So over to you, Bimalendu and Sourav.
Yes, I'm here.
Hi, Bimalendu.
So we have break now.
So we thank all the speakers of this session for keeping time and for giving very exciting talks. I think all of us have learned something. So, Bimalendu, done.
Thank you, Dilip, for chairing the session, and thanks to all the speakers. Sourav, are you there?
Yes. So we meet again at 7 o'clock.
7 o'clock.
Yeah. So maybe ICTS could send out an email saying that the session starts at 7, because explicitly saying that it starts at 7. Because typically we are starting at 8.
Okay.
So we are starting early.
Okay.
So I'll tell them.
Okay.
Okay.
Bye.
Bye.
Okay. Bye, everyone.
Bye. Bye.